Welcome back to the Snoozy Scientist, a calm corner of the universe where curiosity and science drift together to put you to a calm sleep. Tonight, we're slipping beneath the waves to a world right beneath our very feet. The ocean has always been close enough to touch, yet it remains one of Earth's last true mysteries. It covers more than 70% of our planet, but over 80% of it has never truly been explored. The ocean is both vault and mirror, a memory of every age our planet has known, and a reflection of how little we truly understand. Down there, where sunlight disappears long before you've traveled 1,000 meters, many strange things lie hiding, from cities swallowed whole to preserved machines that are older than language. Many histories lie buried so deep that time itself seems to hold its breath there. Every one of our descents and explorations keeps bringing something unexpected, a shape no one can explain, a sound that seems to echo from nowhere, a living light that glows with colors no artist could ever paint. But how much of our planet still remains hidden, even now? What ancient things still sleep in the blackness below, sealed away by pressure and time? And what strange things have we already found down there? Things that have changed what we believed was possible. Tonight, we'll drift into that darkness together, following the trails of real discoveries and real mysteries that prove the sea is still Earth's most alien world. But before we begin, I would love to know where in the world you're listening from and what the time is there. It is always fascinating to think of these stories being heard across so many different skies. If you enjoy these gentle journeys into Earth's mysteries, please do consider leaving a like and subscribing to the channel. A warm thank you as well to those of you who are already subscribed. You're helping this little corner of the internet grow. Now take a deep breath, let your shoulders soften, and together let's descend into the abyss to uncover the strangest things ever found in the ocean. The story of the ocean begins not with a wave, but with steam. When the earth was young, its surface burned with the heat of its own birth. Volcanoes bled fire and gas, and the sky shimmered with clouds of vapor drawn from molten stone. Some of that water had always been part of the planet, locked deep within its minerals. Some drifted in from space, carried by icy fragments that wandered through the early solar system. As the world began to cool, all that vapor fell back in rain that lasted for ages, a downpour so long it carved the first valleys and filled the first basins. The water gathered in hollows and spread across plains of new rock. It rose, fell, and settled again until continents began to take shape. There was no sudden beginning, only the slow patience of time as seas deepened and currents found their paths. In those first ages, the earth turned from a fiery sphere to a blue one, and the ocean became its skin. With water came movement. Winds brushed its surface, stirring the warmth of the sun into waves. Beneath, colder waters crept upward, mixing minerals and gases into a steady exchange that never truly ends. Rain fell, rivers carried silt and salt, and the sea took it all in. Over the ages, this endless circulation became the planet's quiet rhythm, the balance that allowed life to form. But it was not the motion of water that defined the ocean most deeply, it was its memory. Over billions of years, dust and shells settled into soft stone, sealing moments of ancient life inside. A grain of volcanic ash from a faraway eruption, the faint outline of a plankton shell, the whisper of a climate long gone, all pressed together into thin, delicate layers. Each one marked an instant, kept safe beneath the calm weight of the sea. The floor of the ocean became a vast archive of time, written not in ink but in pressure and patience. The first chemistry of life began in that same quiet, in warm shallows and along rocky shores. The sea turned its minerals into experiments. Simple molecules joined, split, and joined again, testing every possible form of persistence. The ocean's motion mixed what needed to meet and sheltered what needed to last. Slowly, within its salt and warmth, structure became pattern, and pattern became life. The sea was both cradle and teacher, shaping each new possibility that drifted within it. As the planet aged, the ocean carried its record forward. The passing of ice ages changed its levels, and the outlines of continents shifted like breathing. Volcanic eruptions and falling meteorites left fine traces across its floor, dust that settled like thin bookmarks between epochs. Creatures came and vanished, leaving their remains as quiet signatures in the layers below. With every tide and every storm, the sea kept adding to its memory, keeping what the land would lose. When humans finally learned to stand at its edge, they saw only the surface. They watched its color change with the sky and learned to follow its moods. For centuries, the ocean seemed unknowable, a restless mirror that reflected clouds and stars, but never revealed what it held inside. Yet curiosity, like the tide itself, never stays still for long. The first attempts to understand the depths began with simple tools, lines dropped from boats, stones tied to cords, careful measurements taken by hand. Those small efforts grew into voyages of study and later into expeditions that carried instruments able to sense the unseen. Scientists began to measure sound, temperature, and light, and in doing so, they started to glimpse the long pages lying hidden beneath. The seafloor turned from mystery into text. Thin cores of sediment were lifted and read like scrolls of time, each layer telling a different story. The bloom of ancient plankton, the trace of a faraway eruption, the faint shadow of a changing climate. What once seemed endless and blank revealed itself as intricate and alive, a memory written in mud and mineral. Every ripple and layer became a quiet page of memory, waiting for those who would one day learn to read the ocean's deep record. And so, beneath the surface where light fades, the sea has continued its work, holding the history of the world within its shifting body and waiting patiently for human hands and minds to uncover it. They called it Heracleion once, or Thonis, the city of Heracles. It stood near the mouth of the Nile, where the river's green waters met the salt of the Mediterranean. For hundreds of years, it was Egypt's vital port, a threshold between land and sea. Ships came from the Aegean and the Levant, bearing wood, silver, olive oil, and stories. Along its crowded quays, priests carried offerings through temple gates, while merchants unloaded their cargoes under the hot, endless light. The air was thick with resin and smoke, salt and grain. Heracleion was not just a harbor, it was a pulse of trade and ritual, a city that lived by the rhythm of tides. But the earth beneath it was never still. The delta was soft, made of silt and shifting sand, and the Nile's great floods laid new layers every year. Slowly, the foundations that had held temples and homes began to change. A tremor would open a crack, a flood would deepen it, and the land would sink by inches that no one noticed. The sea, patient and constant, pressed inward. What had once been firm ground became damp, then soft, then fluid. Streets sank, walls leaned, and the grand colonnades of the temple to Hapi, god of the Nile's bounty, slipped beneath a rising tide of mud. The process took centuries. By the time the city was gone, no one could say exactly when it had vanished. Slow floods and shifting silt buried the harbor over time until its towers lay beneath 30 feet of mud. For nearly 1,000 years the city slept, its name reduced to rumor and confusion on old maps. Fishermen sailed across calm water, unaware that beneath them rested the remains of a civilization that had once greeted kings. The current sealed the ruins in layers of sand and clay, holding them in place while the world above forgot. The silence ended in the year 2000. Frank Gaudiot, a French underwater archaeologist, led a survey team along Egypt's northern coast. They used side-scan sonar to listen to the seabed, sending sound pulses across the mud and recording the echoes that returned. Bit by bit, a pattern appeared on their monitors: straight lines, angles, circles too deliberate to be natural. Divers descended and found columns, statues, and blocks of red granite scattered across the sea floor. The city that myth and maps had misplaced was real, and it was sleeping below the waves. Excavation revealed a world still intact beneath its covering of silt. Massive statues of Hapi and other deities rose from the mud, their surfaces worn but their faces clear. One figure, a colossal queen carved from dark stone, stood nearly 16 feet tall. Another statue, half submerged, showed a pharaoh offering to the gods, his expression as calm as when it was first shaped. Granite temple foundations emerged, their courtyards marked by the bases of columns that once held sacred roofs. Coins and jewelry surfaced too: gold rings, bronze weights, and delicate chains that glimmered faintly in the divers' lights. Among the most haunting finds were the small and personal things: a wooden comb, a scarab seal, fragments of pottery still bearing fingerprints in the clay. Each spoke of daily life that had continued right until the end. In one spot, divers found a cluster of anchors where ships had once tied up, the ropes long gone, but the stones still holding their last positions. It was as if the harbor had simply paused mid-motion and never resumed. The discovery changed what scholars knew of Egypt's maritime history. Heracleion had once been the key to the Nile Delta, its customs and trade offices recording goods from every direction: spices from Arabia, wine from Greece, papyrus bound for Rome. Greek inscriptions mingled with hieroglyphs, and the mix of cultures could be traced in every artifact. The city's dual names, Thonis and Heracleion, proved it had been known to both Egyptians and Greeks, a shared space where two worlds met. Geology explained its disappearance. The weight of new silt combined with minor earthquakes caused the delta plain to subside. The floods that had once nourished the city gradually turned against it, depositing more water than the land could bear. Each season brought a little more weight, a little more movement downward, until the harbor slipped beneath the surface completely. The process was not destruction, but transformation, a slow exchange between land and sea. For nearly 1,000 years the city slept, until the modern world touched it again and the past exhaled. Now, when divers move through Heracleon's submerged streets, they drift between doorways once framed in sunlight. Their lights sweep across statues that once stood in temple courtyards, illuminating eyes that have not seen the sky for a millennium. The city remains quiet, its sounds replaced by the muffled breath of air tanks and the faint hum of machines. Yet in that stillness, its presence feels alive, a complete world folded beneath the water, waiting to be read once more. In the winter waters off Yonaguni, a small island at Japan's far southwestern edge, a local dive guide slipped beneath the waves and drifted toward a cliff that dropped steeply into blue. There, in the quiet dimness, he saw what looked like steps, broad, flat, and deliberate. The formations rose in tiers, stacked like the base of a forgotten pyramid, their edges crisp beneath a film of coral and sand. The guide surfaced with a sense of disbelief, unsure if what he had seen was a quirk of stone or something made long ago. That was in 1986. In the years that followed, scientists, divers, and archaeologists arrived one after another, drawn to the strange geometry of the seafloor. They descended through the shifting haze of light to study the structure that lay about 25 meters deep. Each new dive revealed more: sweeping terraces, angular corners, and long corridors that seemed too even, too straight for nature's ordinary hand. The site extends for nearly 100 meters, carved into the same sandstone that forms the island above. From a distance, it looks like a single mass, a staircase of solid rock descending into the gloom. Closer, It becomes a labyrinth of narrow passages and sloping ledges. Divers glide through these canyons, their lights tracing sharp lines along the stone. When they reach out to touch the walls, their fingers meet smooth planes scored with faint horizontal lines, as if some tool had once passed there. For some observers, the resemblance to architecture is irresistible. The terraces appear like steps. One block juts outward in a shape that could be read as an altar. Another section forms what looks like a processional way. From certain angles, the monument seems to bear the shadow of purpose, a design left behind by people who stood there when the sea was still miles away. But the rock tells its own story. Yonaguni's sandstone and mudstone are layered in beds that break along neat, flat joints. Over millennia, earthquakes, currents, and storms have split and pried the layers apart. Where the bedding planes intersect, they form right angles and terraces, leaving natural steps that appear carved only because the fractures are so precise. Similar patterns can be seen on the cliffs of the main island, where wind and rain have shaped the rock into terraces almost identical to those below the sea. Geologists studying the site have mapped the orientation of these fracture lines. They run parallel to the island's known fault systems, the same cracks that shift when the region trembles. Erosion follows these weaknesses, removing thin layers and leaving the clean geometric faces that draw the eye. To those familiar with the island's geology, the monument is a striking example of nature's patience, an intersection of rock type, tectonic motion, and time. Still, the human possibility lingers. If the sea level was lower during the last ice age, as it was about 12,000 years ago, the Yonaguni shelf would have been dry land. Archaeological remains from the nearby Ryukyu Islands suggest that the Jomon people lived and fished along these coasts during that period. They built with wood and stone, left pottery, and followed the shorelines as they changed. If they walked the shelf that now lies beneath the waves, it is not impossible that they shaped or modified parts of the landscape, carving steps or platforms into exposed rock. The sea later rose more than 100 meters, reclaiming the plains and submerging whatever work might have been there. This uncertainty between erosion and intention is what keeps the site alive in conversation. Yonaguni's steps could be accident or intention, a meeting point where erosion and imagination blur. Each dive adds data, but the ocean adds its own interference. Algae coats the edges, small creatures bore into cracks, and every storm rearranges the sand. Time continues to sculpt the monument, even as humans study it. The divers who visit today describe the site less as a riddle and more as an experience. They move through light that shifts from turquoise to deep blue, their bubbles rising along walls that seem to hum with stillness. The lines and planes of the stone catch the sun in fleeting ways, sometimes appearing almost architectural, sometimes dissolving into shadow and current. There is no single perspective that explains it. Each pass of the light changes what the monument appears to be. Researchers record the dimensions with sonar and photogrammetry, comparing patterns and testing rock samples for signs of human work. So far, no tool marks have been confirmed, yet the geometry continues to provoke the imagination of those who see it firsthand. What makes Yonaguni powerful is not proof or mystery alone, but the coexistence of both. The sense that nature can sometimes sculpt something so exact that it echoes the language of design. Below the waves, the monument waits in a quiet equilibrium between fact and story. The sea moves through its halls, polishing the stone, smoothing the angles, and writing its own slow additions to the surface. The divers drift away, their lights fading into the blue, and the structure remains as it has for thousands of years, unchanged, yet never the same, a monument to the patience of the earth and the persistence of wonder. Far to the north, where the water is dark and heavy with silt, A sonar pulse once touched something that did not quite belong to the plane around it. The sound waves went out, struck the seabed, and came back altered, an echo that drew a small team of researchers to look closer. On their screen appeared a faint round mark, 200 feet across, resting nearly 300 feet beneath the cold surface of the Baltic Sea. Its outline was smooth against the rough seabed, too circular to ignore, yet too coarse to be the work of design. When the team mapped it again, the shape repeated. Instruments picked out a low dome surrounded by ridges, as though part of the seafloor had lifted and then hardened in place. The sonar image showed a structure with regular edges and a shallow central depression, faintly raised from the sediment. To the untrained eye, it looked like a buried object, a disk half covered by centuries of silt. The first reports described it as an anomaly, a simple word that invited every kind of imagination, but the data told a quieter story. Magnetometers swept across the site and recorded faint disturbances, subtle wavering in the field that made compasses twitch. Divers who later visited the area described fine sand shifting over ridged stone and water clouded by particles disturbed from their long rest. Sediment cores showed irregular layering, grains of mixed size and color, evidence that something had once moved through and unsettled the natural order of deposition. To geologists, these small inconsistencies are like notes in the margin of an old book, small but telling. The first explanations looked to natural forces. The Baltic is a glacial basin, carved and filled by the weight and retreat of ice. During the last ice age, vast glaciers pressed down on this region, grinding rock into sheets of sandstone and granite, then dropping boulders the size of houses when the ice melted away. Those boulders are called glacial erratics, and they often settle in patterns that seem almost arranged. The grinding and scouring of ancient ice can also leave circular marks, as meltwater swirls under pressure and cuts grooves in stone. When those formations are later buried by silt and seen again through sonar, their edges can appear uncannily even. Another possibility comes from methane seeps, small vents in the seafloor where trapped gas escapes from deep beneath the sediments. Over time, gas bubbles disturb the mud, pushing upward and creating round depressions. Minerals from the gas harden around the rim, giving the impression of a boundary, almost like the walls of a structure. When currents sweep past, sand collects in the hollows, and erosion rounds the shapes further. Yet, even with these explanations, there remain details that invite more questions. Some divers describe straight grooves, cross-hatched in places where the stone seems fractured into geometric patterns. Others note the texture of the rock, rough but scored with lines that suggest the direction of long-vanished stress. The instruments show gradients in hardness across the surface, hinting that the formation might include different rock types fused together. Each clue can be read in several ways, and each reading adds another layer of interpretation. The sonar itself is partly responsible for the mystery. Sound imaging exaggerates contrast and can turn gradual slopes into sharp edges. In the low visibility water of the Baltic, what looks like a wall may be a simple rise. What seems like a perfect curve may be a trick of shadow. Science proceeds carefully through such illusions, comparing each new scan to the old ones, refining measurements until the noise of interpretation fades and only the consistent facts remain. Those facts are modest but clear. The formation lies roughly 300 feet down. It measures about 200 feet across. It sits on a ridge of glacial rock, surrounded by disturbed sediments that suggest past movement of ice or gas. Magnetometers register anomalies of only a few microteslas, slight enough to be natural variations in mineral content. Samples from nearby show no metal, no engineered alloys, only the usual mix of quartz, feldspar, and clay. When framed this way, the Baltic Sea anomaly becomes less of a hidden object and more of a geological riddle shaped by time and perception alike. The idea that it might be an artifact of human hands has not been ruled out completely, but evidence leans toward a natural origin, a product of glacial sculpting, erosion, and human imagination. It stands as a meeting point where stone, light, and curiosity blur together. For scientists, that is precisely what makes it worth studying. It reminds us that the tools we use, sonar, magnetometers, submersibles, do not just reveal the world, they shape what we think we see. Each reading requires translation, and every translation carries its own margin of mystery. The sea offers patterns, our minds supply meaning. The work of research lies in holding both at once without letting either dominate. In the dim water of the Baltic, the anomaly still sits quietly, touched now and then by divers and currents. The instruments pass over it again each season, drawing new lines, refining the shape, reducing uncertainty by degrees. What once seemed a single image has become a slow study and process, the sound of method catching up to imagination. Far from being a failed mystery, the Baltic Sea anomaly has become something more valuable, a lesson in perception. It shows how easily wonder fills the gaps in knowledge, and how the work of science is not to silence that wonder, but to guide it carefully through what is real. The sonar hums, the data gathers, and beneath it all, the sea continues its patient rearrangement of stone, a silent sculptor whose work we are still learning how to read. Beneath the cold gray waters of the North Sea, the ghost of a forest still stands. Its trees rise from the seabed like sentinels caught in the act of waiting, their trunks thick and dark, their bark still rough beneath a diver's glove. The branches are long gone, but the shapes of oaks and pines remain, roots spread through packed mud that was once soil, and where light filters down, grains of silt drift around them like dust motes in an old house. The silence here is complete, yet it feels full, as though the air of another age is held within the wood itself. In places, whole groves remain upright, their trunks tilted only slightly by the currents. Carbon dating tells us that many of these trees last saw the sun more than 10,000 years ago, when the world was still shaking off the last breath of the Ice Age. Back then, this part of the world was dry land, a broad plain with meadows, rivers, and marshes, where people and animals walked. The trees grew tall and slow, year by year, adding thin rings that recorded each season's balance of warmth and rain. When scientists slice the preserved wood, those rings are still visible, pale and dark, wide and narrow. Each one marks a year, a heartbeat of climate written in cellulose. These forests are fossils of air itself, their rings recording the last breath of an ice age. A wide ring tells of a warm summer, when meltwater carried nutrients into the soil and growth came easily. A narrow ring records a cold, lean year, when frost lingered too long and the sun gave less. In the spaces between those lines, researchers can trace the rhythm of ancient weather, a shifting cycle that mirrors the slow rise of temperature and the restless edge of the sea. When the waters began to move, they did not sweep everything away at once. The sea arrived gradually, in steps and pauses. It carried fine silt that settled like dust on the forest floor, filling hollows and coating roots. The oxygen in the water could not reach deeply into the mud, so decay slowed, then stopped. Bacteria could not thrive there. The trees became sealed in a cold, dark sleep. Millennia passed, and sand covered the old land until it vanished from sight. It is only recently that these forests have returned to view. Storms or shifting tides sometimes strip away the layers that hid them, revealing pale wood beneath the waves. In the North Sea, fishermen hauling nets have pulled up roots and bark, still fragrant with the faint scent of pine. Off the coast of Norfolk, Divers have swum through forests of oak, standing as they once grew, branches broken, but trunks untouched by rot. Far across the ocean, near the mouth of the Mississippi, another ancient woodland lies beneath the Gulf of Mexico, uncovered by hurricanes that cut through the silt and stirred its surface. There, in the Gulf's warm shallows, cypress trunks rise like pillars from the dark, coated with soft marine life, but still bearing the texture of bark. Some are large enough to be centuries old, trees that began life long before the first human settlements in the region. When scientists tested samples from these trunks, they found that the wood still carried traces of resin and cellulose. Carbon dating placed their death near 10,000 years ago, the same moment of planetary change recorded in the drowned groves of the North Sea. Each site is a natural archive, a perfect collaboration between chance and chemistry. The silt preserved not only the wood, but the pollen, seeds, and tiny shells that once fell between the roots. Under microscopes, these fragments reveal the plants that grew nearby and the insects that lived among them. Chemical analysis of the wood shows the air's composition at the time, even the levels of carbon dioxide during the transition out of the Ice Age. From these clues, scientists can piece together a vivid picture of what the world looked like when the coasts were miles farther out and the sea had not yet claimed its present shape. Divers describe the experience as eerie and peaceful. The water dims the color of everything until only shades of brown and blue remain. A gloved hand brushed across the grain of an oak that last felt air before written history began. A fish weaves between the roots, stirring silt that once held leaves. It feels, they say, like walking through time itself, a landscape paused at the edge of transformation. What makes these places powerful is not only their beauty, but their lesson. They show how the earth remembers its own transitions. The coastlines we know are only the most recent chapter of a story that began long before us. The same forests that once grew where the sea now lies remind us that change is constant, but rarely abrupt. The world remakes itself layer by layer, tide by tide. When scientists study the drowned forests, they do not just uncover lost trees, they uncover memory written in wood and mud, a record of how living systems respond to change. The trees that stand beneath the waves today mark a threshold between land and sea, between what once breathed air and what now moves through water. Each trunk is both evidence and witness, proof that time leaves traces everywhere, even in places we thought were gone. In the depths of the Gulf of Mexico, the ocean sometimes folds into itself. Cameras sent down through the blue find a place where the sea appears to have gathered into lakes and rivers. A silvery shoreline ripples faintly below, separating one body of water from another. From a distance, it looks like light playing on glass. But it is not illusion. It is the boundary of a brine pool, a lake of salt water so dense that it refuses to mix with the ocean around it. The edge is clear enough to cast a reflection. Divers describe it as looking down into a mirror that wavers and bends with the slow motion of the sea. These pools form in deep basins where salt deposits, buried long ago, dissolve and seep upward through cracks in the seafloor. The water that emerges is far saltier than the ocean itself, heavy enough to settle instead of rising. It collects in hollows, filling them like ponds on land. The margins of these pools trace pale ridges, sometimes smooth, sometimes broken, as if the ocean floor were learning the idea of a coastline. The temperature and chemistry of the water above and below the halocline, the thin wavering line that divides them, can change within inches. What looks calm is in fact a sharp boundary between two worlds. Exploration vehicles hover at the edges, their lights cutting through the haze. Crabs crawl to the rim, their legs touching the surface as if testing it, and sometimes they slip, tumbling through what looks like air into the heavy brine. The pool ripples once, then stills. The water is so dense that it holds them, and so deprived of oxygen that nothing inside survives for long. The same salt that keeps the pool separate also seals it from the ordinary flow of life. To anything from the open ocean, it is a quiet trap. The name that stuck to one of the largest pools, the Jacuzzi of Despair, was given by researchers watching footage of that slow descent. The title captures both its shape and its stillness. From above, the pool seems to boil faintly, its surface stirred by methane bubbles rising through the brine. Around it, pale bacterial mats spread like lace on dark rock. To the untrained eye, they might seem like patches of decay, but under a microscope, they prove to be dense living communities. Tiny organisms thrive where the chemistry is harshest, transforming methane, sulfide, and other gases into energy. The scene is uncanny. Light bends at the halocline, distorting the shapes of rocks and animals, making the pool look both shallow and bottomless at once. A remotely operated vehicle drifts close, and its sonar maps the basin's dimensions, roughly a few dozen meters across, a few meters deep, resting more than 1,000 meters below the surface. Instruments measure salinity several times higher than seawater, along with traces of hydrogen sulfide and methane that leak continuously from the sediments beneath. The chemical readings suggest that the brine has been trapped for centuries, evolving apart from the sea above. To scientists, these pools are more than curiosities. They are laboratories of isolation, perfect for studying the boundaries of life. Around the rims, bacterial colonies form delicate films that shimmer under camera lights. These films are made of microbes that use chemical energy instead of sunlight to live. They are not the same species that dwell around hydrothermal vents deeper in the ocean, but they share the same strategy, transforming poison into sustenance. It is here that the parallel becomes clear, like the vents far below. Even this lethal boundary shelters life tuned perfectly to poison. The geology of the region explains why such pools appear here and in other deep basins. Thick layers of salt, laid down millions of years ago by evaporated seas, lie buried beneath newer sediments. When cracks open in those layers, the salt draws in water and rises, creating domes and seeps. The fluids that escape are saturated with minerals and gases from the buried strata, carrying the memory of ancient oceans into the modern one. Over time, the chemistry sculpts the seafloor, forming rings of precipitated stone and smooth terraces that outline the edges of the brine. Watching these underwater lakes is like witnessing the planet right in slow motion. Every ripple at the edge, every drift of sediment, is a mark of how salt and gravity carve shape out of formless water. In some places, the pool's surface gleams like polished metal, reflecting the lights of the exploration vehicle in fragments. In others, thin streams of brine spill over low ledges, forming what looks like a flowing river in the dark. The effect is impossible to mistake. The ocean has rivers within itself, liquid moving through liquid, each layer defined by density, temperature, and chemistry. Scientists collect samples from the pool margins with robotic arms. They retrieve fragments of crust and vials of the dense water to test back on the surface. In those samples are the signatures of ancient chemical reactions, the fingerprints of processes that shaped early Earth. Some researchers see these pools as analogs for other worlds, moons like Europa or Enceladus, where liquid water may exist under ice, and where chemical gradients could feed life, just as they do here. The strangeness of these places lies not only in their beauty, but in their quiet contradiction. They are both lake and sea, life and death, isolation and connection. The pools are lethal to most creatures, yet their edges are vibrant, ringed with life that would perish anywhere else. The brine pools remind us that survival is not a single design, but an endless experiment. Every drop that separates itself from the rest of the ocean becomes a new test of what it means to live. When the cameras pull away, the mirror fades back into shadow. The crabs return to the rim, the microbial mats shimmer softly in the dark, and the water above closes in silence. The sea, as always, keeps its secrets with a kind of patience that feels alive. The sound began as a question, a single sharp note in a long, patient listen. Far below the waves, instruments meant to eavesdrop on the ocean caught something that did not fit the usual hum of wind and animals. In the year 1997, a network of listening devices picked up a noise that was so loud it registered across great distances, and for a time the noise became a riddle the world wanted to solve. Hydrophones are like ears for the sea. Anchored to the sea floor, to buoys, or to cables, they record pressure waves that travel through water. Sound moves through the ocean in ways light cannot, slipping along layers, bending with temperature and salinity, and carrying information about events far away. The bloop, as people came to call that curious recording, was a sound unlike a steady whale call or a distant earthquake. It rose in amplitude and then faded, and the pattern made listeners sit up. It was not a whisper, it was a shout that the water carried with surprising clarity. Because the ocean is vast, unusual sounds quickly attract stories. Early listeners and popular reporting filled in blanks with bright ideas. Perhaps it was a creature larger than any known animal, something massive breathing under the sea that humans had not yet met. The idea of an unknown life, of something living and remote and enormous, fit into a long human habit of imagining life where our senses fail us. That hypothesis stirred wonder, and it also moved the public attention and the scientific curiosity into the same impatient orbit. Scientists responded by treating the sound like any other observation, as a clue to be tested rather than a plot to be finished. They compared recordings from different hydrophones to triangulate where the sound most likely began. They examined the frequency, the duration, and the way the sound changed as it traveled. These are ordinary but powerful tools. Sound can be fingerprinted by its pitch, by how it spreads, and by how it interacts with the structures of the ocean. The initial excitement did not mean the work stopped. It only meant that investigators had a reason to look more closely. As more data accumulated, patterns emerged that pointed away from the idea of a single great creature. The characteristics of the sound and the way it propagated aligned more closely with physical events, things like the cracking of ice or the movement of large masses. In polar and subpolar regions, ice behaves like a living material when it breaks. Massive sheets can fracture suddenly, producing low-frequency sounds that travel far underwater. Those cracks can be noisy in a way that is deceptively similar to biological calls at certain pitches. When scientists compared the bloop data to known icequakes and to records of ice shelf activity, the comparison held up convincingly. The identification of the sound as an ice fracturing event did not make the story small. Instead, it shifted the wonder toward the physical world, to the immense forces that shape the planet. Imagine a slab of ice the size of a city snapping along a fault, releasing energy into the sea like an invisible drumbeat. The sound that follows is the ocean's reply, a voice that carries the memory of stress and motion. In that light, the bloop became an example of how the planet announces its changes, and of how listening carefully can reveal processes that are otherwise invisible. Sound is a particularly intimate way to know the sea, because it travels where eyes cannot follow. The same channels that carried the bloop also carry whale songs that cross entire basins, seismic rumbles from distant quakes, and the clicks and shrieks of smaller animals. Hydrophones have revealed that the ocean is not a silent blue, it is a layered chorus, with each source adding its voice to the whole. A crack of ice here, a whale call there, a submarine volcano in another place. Together they make an ongoing symphony that records weather, geology, and life. That recording showed too how quickly imagination moves in the absence of method, and how method reassures us with evidence. The early talk of mysterious beasts was not wrong in spirit. A mysterious sound invites imaginative thought. The value of the subsequent investigations lay in their patient narrowing of possibilities, their steady use of instruments and comparisons. Hearing led to measuring, and measuring turned story into knowledge. There is also a human tenderness to this kind of work. Technicians and researchers spend long nights with headphones on, scouring spectrograms and writing notes. They calibrate instruments, they correct for biases, and they work to separate the signal from the noise. In their careful work, the ocean becomes legible in a way it had not been before, and each solved mystery becomes a model for how to approach the next unknown. The ocean's voice carries far beyond what the instruments first captured. Each new recording folds into the next, filling the sea with shifting frequencies that never quite repeat. Somewhere out there, another sound begins, faint and waiting, moving through layers of water toward another set of listening ears. For centuries, the sea carried stories of a creature no one could prove, but everyone could picture. Sailors spoke of something vast and quiet, something with arms that could reach the deck of a ship and pull a man away before he could shout. They called it the Kraken in some places, in others it was only the giant, a shape half seen beneath breaking waves. Most scientists of the past dismissed it as a trick of light, an exaggeration made larger by fear and by the endlessness of the ocean. Yet the stories lingered, because stories often wait for evidence to catch up. The evidence arrived slowly. Now and then a fisherman in the high latitudes would bring up a tentacle tangled in a line, or a beak too large to belong to any known species. The flesh was pale, soft, and full of ammonia that kept it from freezing in the cold. It was enough to show that something of great size was out there, but not enough to describe it. The deep sea does not give up its inhabitants easily. It keeps them in pressure, in dark, in a cold that dulls sound and movement. For a long time, that quiet kept the colossal squid hidden. Then, in the early 2000s, cameras finally reached the depths where these animals live. Remotely operated vehicles moved through black water and caught images that were both alien and strangely elegant. The squid drifted, its fins moving with slow pulses, its body long and pale like a drifting sail. When light struck its eyes, they reflected back as bright disks, each one the size of a dinner plate. No other creature on earth has eyes so large. They are built to gather what little light filters from above and what faint glows come from the creatures around it. With those eyes, the squid can see shapes that no other predator can see, shapes that might mean food or danger in a place where light barely exists. Its tentacles are lined with rotating hooks and suckers that can twist and lock. These are not tools for show, they are adaptations to hold struggling prey in a world where even small creatures are slippery and fast. The hooks rotate to maintain grip, a mechanical wonder formed entirely of living tissue. Each arm is muscular and controlled by a nervous system that allows independent movement. The result is a kind of living machine, efficient and precise, built not for chaos but for survival. The colossal squid lives in the freezing waters of the Southern Ocean, where temperature and pressure create a world apart from the rest of the sea. Here, food is scarce, and the cold slows metabolism to a crawl. Growing large becomes an advantage. In the deep, bigger bodies lose heat more slowly, and size allows for energy storage that small animals cannot afford. This pattern, called deep sea gigantism, appears in many species: amphipods the size of mice, jellyfish with tentacles longer than buses, and isopods that look like armored relics from another age. The colossal squid is the largest known invertebrate, but it follows the same quiet rule. The deeper you go, the stranger and larger life becomes. When scientists study the physiology of this squid, they find adaptations that speak to both patience and violence. Its beak, sharp and curved, can slice through fish and smaller squid with ease. Its muscle fibers are tuned for short bursts of power rather than endurance, fitting for an ambush predator. Its stomach, when examined, sometimes holds fragments of Antarctic toothfish, proof of battles fought in the cold dark where no one watches. The squid's blood is filled with copper based molecules called hemocyanin, better at carrying oxygen in low temperatures than the iron based hemoglobin found in mammals. Every detail is a note in the same melody of survival. Finding the colossal squid did more than confirm an old story. It reminded people that myth and science are not enemies, but stages of the same curiosity. Long before anyone filmed one, the sailors' descriptions were not entirely wrong. The enormous eyes, the strength of the arms, the sense of something ancient and hidden, all were real, just waiting to be seen clearly. What imagination created in fear, observation, later filled with detail. The creature that once symbolized terror became instead a lesson in adaptation and endurance. Even with footage and specimens, much about the squid remains unknown. No one has yet observed its full behavior in the wild, or how it hunts, or how it finds a mate in the open dark. Every glimpse so far has come from accidental encounters, from lines and nets, from cameras passing through by chance. The sea still keeps most of its privacy. Each discovery leads to new questions, and each question pulls scientists deeper into the cold southern waters where the next image might wait. The colossal squid holds a kind of balance between legend and biology. It shows how imagination often runs ahead of evidence, but also how patient attention can turn fear into knowledge. The same creature that once haunted stories now fills them again, not as a monster, but as proof that the world is still full of things larger and more complex than we expect. Its eyes remain open in the dark, silent witnesses to a realm that has only begun to be understood. The sea around Antikythera is a narrow channel of deep blue glass, a quiet stretch between Crete and the Greek mainland. In the spring of 1900, a storm drove a group of sponge divers to shelter there. When the winds eased, one of them descended, weighted and slow, into the still water. He expected the bare rock of the Aegean seafloor. Instead, his lamp caught the gleam of bronze and the pale curve of a marble face staring up through silt. When he surfaced, gasping through his heavy suit, he could only say one word: statue. The discovery drew more divers, and beneath them a whole world came into view. Fragments of armor, amphorae, and broken sculptures lay scattered across the slope of a sunken ship. Its timbers had long dissolved, leaving a cargo field of fallen history. Among the bronze torsos and collapsed pottery, there was something small and irregular, a lump of green corrosion that looked more like a rock than a relic. The divers collected it with the rest, unaware that they were carrying to the surface one of the most intricate objects ever made in the ancient world. That fragment, once cleaned, broke apart into dozens of smaller pieces. Inside them, faint teeth appeared, tiny interlocking gears, worn but unmistakable. Under layers of mineral growth lay precision, ratios, and design. The object would come to be known as the Antikythera mechanism, a machine 2,000 years old, built to turn the sky into mathematics. Each fragment revealed more of its secret structure. Thin bronze plates bore faint inscriptions, Greek letters so fine they could only be read under magnification. Some marked calendar months, others described eclipses and planetary paths. When experts began to fit the pieces together, they found a system of more than 30 bronze gears, each with hand-cut teeth no wider than a fingernail. These gears, when connected, recreated the complex dance of the sun, the moon, and the planets known to the ancient world. The ship that carried it likely sailed in the first century before the Common Era, a merchant vessel laden with statues, glassware, and luxury goods. Somewhere between Rhodes and Rome, a storm tore it apart. Its cargo spilled into the sea, settling into sand and darkness. The bronze turned fragile over time, not destroyed, but transformed, its surfaces eaten away until only the internal geometry remained, like lace made of minerals and memory. Every curve of metal recorded both the hand of its maker and the slow patience of corrosion. When modern researchers revisited the mechanism, they brought instruments finer than any chisel or brush. X-ray tomography and high-resolution surface scans turned the fragments into translucent models. Within those digital cross-sections, hidden lines and gear trains reappeared. The scans revealed not only the arrangement of the wheels, but also the exact gear ratios, ratios that matched the cycles of the moon's orbit, including its slight acceleration and deceleration as it travels around Earth. Other dials showed the calendar of ancient Greece, the rising and setting of stars, and even the schedule of the Olympic Games. Each image felt like watching thought take shape again. What had been mute corrosion became a blueprint for how knowledge once moved, through hands, metal, and observation. Every scan drew the ancient machine closer to thought, proof that brilliance can survive even when memory cannot. No one can say exactly who built it. Some attribute its design to the school of Hipparchus, the astronomer who mapped the heavens from Rhodes. Others see the geometry of Archimedes or his successors in its structure. Whoever made it understood the sky, not as myth but as mechanism, where beauty lived in precision. To them, the heavens could be measured and predicted through the turning of bronze, just as one might measure distance by pacing the ground. The Antikythera mechanism changed what scholars believed possible of ancient technology. For centuries, no comparable device existed. Europe would not see similar clockwork until more than a millennium later. Yet here, in the wreck of a merchant ship, lay a complete cosmological model, small enough to rest on a table, designed to translate celestial movement into motion the hand could feel. Each tooth of each gear carries the rhythm of an ancient mind, mathematicians, artisans, and philosophers working together in quiet workshops lit by oil lamps. The mechanism was not just a tool, but a bridge between observation and belief, a physical conversation with the sky. Now it rests in a museum in Athens, its fragments sealed behind glass. X-rays still peel back its layers, and new fragments are occasionally found on the seabed where the original ship broke apart. Divers say that the statues nearby seem to keep watch, their stone faces softened by time, their eyes turned toward the device that once measured the stars. The bronze gears no longer turn, but their design still moves through time. They remind us that human ingenuity has always reached for the same thing, the wish to understand the order behind the shifting lights above. Somewhere in that dark water between a broken hull and the slow drift of silt, the first computer still whispers its equations to the sea. From the air, the lagoon looks like a painter's dream, rings of turquoise, coral shadows curling inside the calm. But beneath that still surface lies a city of metal and silence. Truck Lagoon, now called Chuk, holds more than 50 sunken ships, each one resting quietly in the blue. They are not ruins in the usual sense. They are entire lives paused mid-motion, engines caught mid-turn, porcelain cups still balanced on tables that have not moved in 80 years. In February of 1944, this was one of the most fortified harbors in the Pacific. The Japanese Imperial Navy had turned it into a floating fortress. Fuel ships, supply vessels, submarines, and destroyers crowded the shallows. For 2 days, the calm broke. American aircraft came in waves, dropping bombs that shattered decks and tore open hulls. Oil slicks burned on the surface, fire turning water to mirror. By the end of Operation Hailstone, the lagoon was a graveyard of steel. The sea closed over it as if tucking it in. When divers first returned decades later, the ships were still there, upright and almost serene. Many sat perfectly balanced on their keels, their guns pointing uselessly into shadow. The air inside their cabins had long been replaced by water, but everything else, the radios, the tables, the boots, remained where human hands had left them. Inside one transport, a row of teacups sits along a shelf, each outlined by rust and silt. Nearby, a gas mask floats half buried in fine sediment, its glass eyes dim in the filtered light. In another ship, a control panel lies tilted on its side, dials still frozen at their last readings. A typewriter rests upside down on the floor of an office. A pair of boots stands neatly at the edge of a bunk. Every object, no matter how small, feels deliberate, as if someone stepped away only moments ago and never returned. The machinery, too, still tells its story. Engines lie open to the sea, turbines heavy with coral, iron bulkheads have softened under salt, their paint long since given way to textures of orange, green, and blue. Over time, coral larvae found their grip on these surfaces. Marine biologists studying the site have recorded hundreds of coral species, with the earliest colonies forming within a decade after the wrecks sank. The rate of growth depends on the material. Steel invites faster settlement than aluminum, its microtexture providing a better anchor for coral polyps. Slowly, metal became reef. In some parts of the lagoon, bright sponges and delicate sea fans frame gun turrets. Sea anemones wave gently inside ammunition boxes. In others, soft corals climb up bridge ladders like vines reclaiming a forgotten garden. Crabs patrol empty corridors. Shrimp take shelter in hollow barrels. Fish dart through open hatches where sailors once walked. Engines once meant for battle now hum quietly with shrimp and coral, history breathing through rust. Light filters through the water in long, slanted beams. It moves across decks, catches on propellers, and slides through portholes, painting shifting shapes on the sand below. Divers who swim here describe the sensation as walking through time rather than through space. The silence is not empty. It feels filled with the slow ticking of decay and growth, the quiet arithmetic of life returning to what was once built for war. Some wrecks are shallow enough that coral gardens spill up toward daylight, while others lie deep in the still blue below 200 feet. On these deeper ships, the water is cooler, the coral paler, and fish gather in thicker, slower schools. The deeper wrecks have aged differently, slower corrosion, less algae, and a sense of stillness that borders on sleep. Scientific teams catalog each site with ROVs and sonar, studying how the metals decay and how ecosystems take shape on artificial reefs. Every ship tells a different ecological story depending on depth, current, and exposure, and yet, amid the quiet work of biology, the human traces persist. A porcelain bowl still bears the red symbol of its maker. A compass sits in its cradle, its glass cracked but its needle faintly visible. There are no names on these objects, only gestures, hands that held them, voices that once filled the rooms where they now rest. The lagoon holds its history without sentiment. It does not preserve, it integrates. Rust becomes reef, memory becomes mineral. The ghost fleet is not only a museum or a tomb, it is a living laboratory. Scientists measure oxygen levels near the wrecks and compare them to nearby reefs. They trace how metals leach into sediment and how new life adapts around it. Some coral species even grow faster on steel hulls than on natural limestone, their skeletal structures richer in iron. The line between artifact and habitat blurs until they are the same. From above, the lagoon gives no hint of what lies below. Only the occasional shadow of a diver's bubbles breaks the surface. Beneath, the ships remain, silent but not lifeless, enduring but not unchanged. What was once the language of war has turned into the syntax of growth, spoken in choral and current instead of gunfire. The sea, as always, continues its patient work, turning history into habitat, one grain of silt at a time. At the bottom of the ocean, far below the last trace of sunlight, the planet exhales. Cracks in the seafloor open and close with the slow rhythm of the Earth's crust, and through them boiling water rises from the rock. The heat below is fierce, born from magma that never sees the surface. Seawater forced through fissures reacts with the minerals it touches, gathering metal and sulfur until it emerges again, thick and dark. The result is a column of superheated fluid, a plume that pours upward into the cold. These features are called black smokers, volcanic vents that do not erupt flame, but breathe clouds of metal and steam into the abyss. The water leaving a vent can climb above 370 degrees Celsius, yet it does not boil. The pressure here is overwhelming, the weight of miles of water holding everything in place. Only a few feet away, the temperature falls to near freezing. Between those extremes, life has found a foothold. The shimmering haze where hot water meets cold becomes the edge of another kind of world. When explorers first reached these vents in the late 1970s, they saw what no one expected to see: abundance in a place with no sunlight. Submersible lights cut through the black, showing towers that rise like cathedrals of stone, and at their bases, entire communities pulsed with motion. Pale crabs scuttled over mineral ridges. Shrimp and limpets clung to vent mouths. Standing like sentinels in the heat were giant tube worms, white as bone, each capped by a red plume that waved slowly in the chemical currents. These animals live on chemistry itself. Deep inside the tube worms, colonies of sulfur-eating bacteria turn hydrogen sulfide into food, feeding their hosts from within. Mussels and clams host similar symbiotic microbes. Together, these partnerships form the foundation of an ecosystem driven not by light, but by reaction, a slow, invisible alchemy where elements meet and life begins again. Around the vents, the rocks are carpeted in microbial mats, pale veils of bacteria that shimmer under the submersible lamps. The vents build themselves as chemistry, and flow conspire. Superheated water, rich with dissolved metals, cools as it meets the surrounding sea and releases iron, manganese, copper, and zinc. Those minerals fall like dust and solidify, stacking into chimneys that can tower several stories. Over time, chimneys collapse and regrow. Some bear black coats of iron sulfide, others show orange hues from oxidized minerals. Each structure is temporary, erected by chemistry and altered by the very forces that made it. The plumes drift upward like smoke, spreading mineral grains that seed distant places. The water around an active vent shimmers with suspended particles. Chemical analysis of vent fluids shows extreme acidity in places, with pH measurements that may fall near 2, and concentrations of dissolved metals that would be toxic to surface life. Yet these reactions create molecules that bind carbon and nitrogen, some of the same building blocks that may have helped the first living cells assemble on early Earth. In that way, the vents are both habitat and laboratory. Life here is shaped to exacting tolerances. There are snails that wear armor of iron sulfide, bacteria whose enzymes operate at temperatures higher than boiling at surface pressure, and ghostly shrimp that detect faint gradients of heat and chemistry. Many vent species complete life cycles on rapid timescales because a vent may remain active for only a few centuries before cooling and forcing its community to disperse. Larvae drift on deep currents, searching for the chemical signatures of a newborn smoker, and when they find it, they settle and begin again. That pattern repeats, a heartbeat stretched over geological time. Scientists measure these worlds with precise instruments. Temperatures, chemical concentrations, and mineral compositions are logged and sampled. Sediment and fluid analyses reveal cycles of growth and decay, the rise and collapse of mineral towers, and the flow of elements between crust and ocean. The iron-rich plumes stain the surrounding water and form nodules and crusts across the floor. Each expedition returns traces that sharpen our understanding of how elements cycle at the interface of rock and sea. If such chemistry can build worlds here, perhaps it can elsewhere, sealed beneath ice or stone. The vents provide the best earthly analog for oceans hidden beneath frozen shells, for moons where tidal heating might stir the deep. That parallel is not mere fancy, it is a concrete idea grounded in thermodynamics and geochemistry. Expeditions continue to find surprises. New species appear, odd behaviors are recorded, and mineral formations are seen in stages previously unobserved. The scene is elemental rather than familiar, stone and steam, metal and microbe, yet it is full of life engineered by the narrow spaces where heat and chemical richness meet. Far above, the surface of the sea slips on in light and weather that will never reach these chimneys. Down here, among the pillars and plumes, the vents keep working, emission by emission, building and unbuilding in the darkness. The black smokers hum and shift, and the communities that depend on them carry on in the slow, precise ways that deep time allows. In the open waters of the Philippine Sea, far beyond the reach of sunlight, a small ship lies where it fell nearly 80 years ago. It rests almost 7,000 meters below the surface, deeper than any other wreck ever found. The USS Samuel B. Roberts, once a destroyer escort built for speed and courage, now sits in a world where the weight of the ocean could crush steel like paper. Its story began in battle, but it continues now in silence, folded into the stillness of the deep. When the ship went down in 1944, the war above the Pacific was fierce and endless. The Samuel B. Roberts fought as part of a small group of American vessels that faced an overwhelming Japanese fleet off the island of Samar. Outgunned and outnumbered, her crew charged forward anyway, firing until the last shell was gone. Many of those aboard were young, their lives barely started, their bravery larger than their ship. The battle raged in smoke and fire, and when it was over, the sea claimed what remained. The ship sank to a place no human could reach, leaving only stories carried by survivors and ripples that vanished into the horizon. Decades later, as technology caught up with curiosity, explorers began to search for what had been lost. The ocean floor is not a gentle landscape, it is a range of trenches, cliffs, and plains shrouded in permanent night. Mapping it requires patience, precision, and machines built to survive a world where pressure rises to more than 1,000 times that at the surface. Each descent into such depths is an act of trust between engineers and the machines they build. The search for the Samuel B. Roberts took years of scanning, studying, and narrowing the possibilities. In 2022, the wreck was finally found by a deep-sea submersible piloted by explorers who knew they were pushing the limits of what humans had ever done beneath the waves. At that depth, a mistake can mean the end of everything. The water weighs down on every bolt and seal, turning metal fragile, turning human breath into something precious. Yet the submersible reached the site, and for the first time since the war, light touched the ship again. The cameras showed a shape barely recognizable at first. The hull was twisted, the bow separated from the stern, and the deck guns were frozen mid-aim. Layers of sediment had gathered in the years since, painting the ship in tones of brown and gray, but the structure was still there, remarkably intact despite the unimaginable pressure. The deep sea, in its own way, had preserved it. At that depth, decay slows almost to a stop. There are no strong currents, no scavengers, no oxygen rich water to corrode the metal quickly. The cold and the darkness act like guardians, keeping the wreck as it was when it fell. Pressure has warped some parts of the ship, bending steel that once defied storms. Beams curve slightly where stress built up over the decades, like the ribs of a great animal resting in the dark. Yet the outlines of the vessel remain. Even the gun mounts and sections of the hull are recognizable. The deep, with all its crushing force, also knows how to keep its secrets intact. Explorers who have seen the footage describe the atmosphere as otherworldly. The ship sits on a slope of soft silt, tilted as if still trying to move forward. Around it, the water is empty and still. No fish drift by, no coral glows in the light. The only movement comes from the faint currents stirred by the submersible's thrusters. Every sound is distant and soft, like echoes caught in a dream. Finding the Samuel B. Roberts was a technological triumph. Reaching nearly 7,000 meters required machines that could endure pressures no human body could withstand. The vessel that carried the explorers was small, designed for endurance rather than comfort. Its lights reached only a few meters through the thick blackness, revealing the ship one piece at a time. The sight was not grand or dramatic. It was quiet, almost reverent. What technology achieved was not conquest, but connection, a way of seeing history where no eyes had seen it before. The wreck sits there now, far from the noise of the world above. It is neither forgotten nor alive, resting in a kind of suspended time. The sea around it does not stir easily, and the silence is deeper than anything humans can imagine. In that silence, every piece of the ship becomes a fragment of memory. A torn hull, a bent propeller, a rusted gun barrel, each one holds a trace of the people who once stood there, the shouts and the heat of battle replaced by the slow drift of sediment. The Samuel B. Roberts remains one of the most remote human artifacts on Earth. It lies where light has never reached naturally, where even sound fades quickly. The deep sea does not distinguish between metal and stone, between history and geology. It accepts everything into its slow, steady rhythm. Above it, storms cross the Pacific, and ships still travel those same waters. Below, nothing changes. The wreck endures, quiet and untouched, waiting in the pressure and the dark, a piece of human history preserved by the weight of the sea itself. At the heart of Antarctica, there is a silence so deep it feels older than the air itself. The wind moves across a plain of white that never melts, and beneath that frozen expanse lies something hidden, sealed under more than 2 miles of solid ice. It is a lake, vast and ancient, trapped away from the world for millions of years. No sunlight has ever reached its surface. No storm has stirred its waters. Lake Vostok is a pocket of liquid time, a secret the planet has kept under pressure and cold. The lake was first discovered not by sight, but by signal. In the 1950s, scientists studying radar reflections from the Antarctic ice sheet noticed a strange echo coming from far below. Instead of scattering like it would from solid ground, the radar beam returned smooth, as though it had struck a mirror. It took decades of surveys to confirm that the reflection came not from rock, but from liquid water. Warmth rising from the Earth's crust and the crushing weight of ice above it had combined to keep a buried lake from freezing solid. The finding was extraordinary, a body of water locked in isolation since long before the first human ancestor had drawn breath. For years, no one dared to touch it. To drill carelessly into something so old risked destroying what made it valuable. If modern microbes were to fall into those ancient waters, they could erase what had survived untouched for eons. So the world's scientific community debated, planned, and built technology capable of approaching the lake without bringing the surface down with it. The protocols became as strict as those used in space missions. Equipment was sterilized, lubricants replaced with inert fluids, and sensors sealed within protective casings. The idea was not only to reach the lake, but to arrive without leaving a fingerprint. In 2012, after more than 2 decades of preparation, a Russian team drilled through the final meters of ice. Their instruments dipped into water that had not met the open sky in perhaps 15 million years. When samples were carefully drawn upward and frozen for study, what they revealed changed everything known about isolation and endurance. Inside the meltwater were living cells, tiny bacteria moving slowly, methodically, as if time itself had taught them patience. Their DNA held genetic sequences never before catalogued, patterns suggesting long, uninterrupted evolution separate from the rest of Earth's biosphere. Some of the microbes appeared to rely on chemical reactions between rock and water, drawing energy from the slow release of minerals beneath the lakebed. Others carried genes that hinted at mechanisms to repair radiation damage or to survive on almost no nutrients at all. Each discovery whispered the same truth. Life had not merely persisted here, it had adapted in ways the surface world could barely imagine. The environment of Lake Vostok is as alien as any place on Earth can be. The water is saturated with dissolved gases, its pressure immense, its oxygen levels far higher than those of surface lakes. No photosynthesis occurs in the dark. Energy moves instead through chemical gradients, where rock meets liquid, and small communities of cells gather around those invisible boundaries. The water itself is warmed only slightly, held at about 30 degrees Fahrenheit by geothermal heat seeping upward from the planet's crust. Above, the ice acts as a lid and a lens, pressing down with a calm that has lasted longer than recorded history. Each time scientists study samples from the lake, they find something new: proteins that remain flexible in near freezing water, cellular membranes reinforced against crushing pressure, DNA that carries traces of repair, like scars of long endurance. These findings do not simply expand biology's list of extremophiles, they deepen the understanding of what persistence looks like. The organisms in Lake Vostok are not thriving in any human sense, they are surviving in the truest one, trading growth for longevity, speed for stability. Drilling into the lake remains one of the most carefully monitored scientific efforts on the planet. Every entry point must be sealed after use, allowing the ice to close again naturally. The meltwater used for sampling is sterilized, filtered, and refrozen to prevent any contamination of the ecosystem below. Each time, the lake returns to its silence, undisturbed, as if nothing had ever touched it. The idea is simple but profound: to learn without breaking what has endured on its own for millions of years. Standing above that buried sea, one might not imagine the complexity waiting below. The surface is a desert of ice, temperatures falling below minus 100 degrees Fahrenheit, winds carving lines into snow that will never melt. Yet far beneath that lifeless plain, bacteria stir in quiet motion, carrying genes older than the continent's current shapes. In their slow metabolism and unhurried cycles, they keep the memory of an ancient Earth alive, a version of the planet before mammals, before forests, before even grass existed. In silence and ice, the planet keeps a secret no storm can reach. Lake Vostok remains one of the last untouched places in the known world, its water heavy with stories written in chemistry instead of words. Within that darkness, life continues not because it must, but because it can, a small and steady light moving beneath miles of frozen sky. Beneath the gray waves of the North Sea lies a memory of dry land. It was once a landscape of rivers and grass, forests and marsh, stretching between what we now call Britain and the European mainland. Long before it drowned, the place was alive with sound: the soft calls of migrating birds, the heavy tread of mammoths, the crack of flint against stone as people shape their tools beside a river that no longer exists. Today, it is called Doggerland, though its true name, if it ever had one, was lost when the sea came in. The land was never barren. Archaeologists picture it as a vast low country of rolling meadows and wooded valleys, rich with game. Birch, pine, and willow stood along shallow streams. Red deer grazed near clear pools where families of early humans fished and camped. When trawlers drag their nets through the shallow banks, they sometimes bring pieces of that forgotten life back up into daylight. Bones of aurochs, darkened by the centuries, polished antler points, worked flint blades as sharp as the day they were made. Once, a trawler net snagged the tusk of a mammoth. Another time, it caught the skull of a woolly rhinoceros. In the folds of mud on the deck, the past sometimes arrives uninvited. Each of those objects tells the same quiet story that humans once walked where the tides now rise and fall. The first hunters and gatherers crossed Doggerland without knowing it was temporary. To them, it was simply a place of abundance, a link between coasts, a path lined with rivers that fed into the ancient North Sea basin. They followed herds across open plains, moved their camps with the seasons, and left behind the traces of fires, tools, and bone fragments that would one day rest under silt. Archaeologists can now trace where those people once lived by reading the seafloor as though it were a buried map. Sonar and seismic scans reveal the ghost of valleys and ridges beneath the mud. You can still see where rivers carved channels that joined to a great estuary and where lakes once glimmered under northern sun. The outlines are delicate but clear, a topography preserved in silence. Between these ghostly riverbeds, scientists have taken cores of sediment that still carry pollen, birch, pine, hazel, evidence of a temperate world, greener and softer than the one above it now. Each layer of that sediment holds a different chapter in the slow passage from grassland to sea. The people who lived here would have noticed the world changing long before it disappeared. Storms came more often, salt crept into freshwater marshes. What had been firm ground turned to mud. Floods that once receded began to linger, but to those watching from the edges of their camps, the transformation must have seemed too slow to grasp. No single event marked the end. It happened over generations, as water claimed the low places first, then the rivers, then the wide plains between. At last, a single violent moment sealed what centuries had begun. Off the coast of Norway, a massive underwater landslide, the Storegga Slide, sent a wave surging across the North Atlantic. It was a tsunami, unlike any seen since, its energy sweeping across the northern coasts. For the people of Doggerland, it must have been unthinkable. The sea rushing inland, forests bending and breaking, rivers reversing their flow. When the water retreated, much of the land was gone. The survivors would have looked out over a world remade, islands scattered where valleys had been, marshes turned to inlets, the horizon no longer green, but gray and restless. What followed was retreat, not extinction. Families moved inland, following animals and the promise of safety. They carried flint, fire, and memory. Some of their stories may have endured, reshaped into the old European myths of lost lands swallowed by the sea. Those stories, passed through generations, became echoes of something real, of people who once stood where ships now pass, watching their home dissolve into tide. Beneath the seafloor, their world is still there in outline. Sonar scans trace the buried meanders of rivers, and divers recover pieces of bone carved with human marks. The remains of forests lie preserved under layers of silt, trunks dark and solid when pulled from the seabed. In laboratories, scientists date these finds with carbon and isotope analysis, matching them to a time when reindeer grazed near the Thames and elk wandered through what would become the North Sea. Doggerland's story is not a warning so much as a reminder that the land and the sea are never finished drawing their borders. Coastlines are moments, not boundaries. The waves that seem eternal are only the latest shape of a restless ocean. Today, the fishermen who work these waters know the map above, but not the one below. Beneath their keels lies a country of silence and memory, a landscape where forests turn to mud, and mud turned to sand, and sand to sea. Once there were fires burning under the same sky that shines on waves now. Once there were voices speaking across a plain, where now the wind passes over open water. Their world vanished beneath waves that seemed eternal, though the sea itself was only changing shape. In the farthest depth of the sea, where darkness presses so completely that even sound feels slower, a pale creature moves through the cold like a drifting thought. It is small, no longer than a human hand, yet it lives in a place that would destroy nearly every other form of life. The Mariana snailfish glides quietly along the trench floor, a shape almost without weight, its body so translucent that the faint shimmer of organs can be seen beneath the skin. It is not armored, not strong, not fast, and yet it thrives deeper than any fish known to science. The snailfish's strength lies in softness. Instead of resisting the immense forces around it, it yields. Its body has no air-filled spaces, no gas bladder that would collapse under pressure. Its bones are light and flexible, more like hardened threads than rigid supports. The skull is open in structure, built not to fight the compression, but to flow with it. Even its muscles carry extra water, turning what would be a burden for most animals into a natural equilibrium. In the trench, rigidity is the enemy. Survival belongs to what bends. Its skin is so thin and clear that it seems sculpted from the sea itself. The faint outlines of veins and organs show through, like ghostly brushstrokes under faint light. There are no scales, no rough edges. The smooth, gelatinous surface allows the fish to move without resistance through the dense water. Inside, its cells hold special molecules that act as stabilizers, chemical scaffolds that keep proteins from folding or tearing apart. One of these molecules, trimethylamine N oxide, accumulates in greater amounts the deeper a snailfish lives, countering the crushing force that would otherwise deform the machinery of life. Each microscopic adjustment becomes part of a delicate design tuned perfectly to the deep. In this strange architecture, everything has been pared down to what is necessary. The eyes are small, sensing movement and contrast rather than light. The mouth is modest, shaped to catch small amphipods that drift in the slow current. The digestive system works patiently, extracting every fraction of energy from each meal. Its heartbeat is steady and minimal, conserving strength in a world where waste is a luxury. Every function has learned to do less, but to do it perfectly. When scientists first captured footage of the snailfish swimming at the bottom of the Mariana Trench, they were struck not by its fragility, but by its calm. It moved with the fluid grace of something that belonged utterly to its surroundings. Around it, a thin snow of organic matter fell from the surface world above, fragments of plankton, bits of shells, and the remains of creatures long dead. From this slow rain, the snailfish gathers life. The energy of the sun, once trapped in the bodies of distant organisms, drifts down through miles of darkness and ends here, feeding a creature that has never seen light. In laboratories far from the sea, biologists study the snailfish not as a curiosity, but as a model of adaptation. Its tissues hold secrets that help engineers understand how to create materials that remain stable under extreme pressure. The way its body balances flexibility with form, soft but structured, yielding but precise, mirrors what designers attempt in deep diving submersibles and robotic arms built to explore trenches where metal can warp. The snailfish's design, shaped by evolution and patience, becomes a kind of living equation in resilience. And yet, despite this perfection, it is not invulnerable. Scientists who bring specimens to the surface find that the same adaptations that allow it to live at crushing depths become fatal when pressure is removed. The fish's body loses shape almost instantly, its fragile tissues collapsing into stillness. The creature cannot survive our world any more than we could survive its own. It belongs entirely to that hidden layer of the planet, the deep that never stirs, the black water that hums softly with ancient heat. In recent years, remotely operated cameras have followed snailfish as they weave through the cold haze near the trench floor. They are never seen in groups. Each moves alone, tracing a slow, deliberate path over the rippled silt. Sometimes a faint current stirs the fine sediment, and their outlines waver, dissolving briefly into the dark. Then, as the flow settles, they reappear, small ghosts, weightless, unhurried. The ocean's deepest places are not barren, as once thought. They are slow worlds, worlds of endurance rather than abundance. Here, even breathing becomes an act of balance. The snailfish has no armor, no weapon, no light, only adaptation, the quiet art of fitting perfectly into the impossible. If technology has learned anything from these depths, it is that survival is not always strength but understanding. The snailfish's body speaks that truth wordlessly. Its form endures not by fighting the pressure, but by matching it, turning fragility into mastery. Far below the last reach of sunlight, beyond the limits of sound, the snailfish continues its slow, unbroken motion. Its world is one of perpetual night, a realm where time itself seems to move differently. There, in that silence, life has not just endured, it has found a rhythm the planet itself keeps, deep and steady, perfectly tuned to the weight of the sea. In the quiet blue folds of the Mediterranean Sea drifts a creature so small it could rest on your fingertip. It is almost invisible, its body a bell of clear tissue, pulsing gently like a heartbeat made of light. This is Turritopsis dornea, the immortal jellyfish, a being that seems to have found a way to escape the ordinary laws of life and death. While all other creatures move in one direction, from birth toward an end, this jellyfish can reverse that path, turning time back upon itself until the cycle begins again. It starts its life like most jellyfish, as a larva that settles on the seafloor and grows into a small colony called a polyp. From that colony, tiny jellyfish bud and break free, rising into the water to drift and feed and glow. Normally, this would be the last stage, the adult form that ends in age, injury, or being eaten. But Turritopsis has another option. When threatened by stress, starvation, or physical harm, it can change its body completely. Instead of dying, it sinks back to the seafloor and transforms, becoming young again. This process, known as transdifferentiation, is one of the rarest tricks in nature. In most animals, a skin cell remains a skin cell forever. A nerve cell remains a nerve cell, each locked into its role. The immortal jellyfish breaks that rule. When the adult begins to weaken, its cells melt their identities and return to an earlier, more flexible state. A nerve cell can become muscle, a muscle cell can become skin. It is as though the creature erases its own history and writes a new one using the same materials. Under a microscope, the change looks like slow motion rebirth. The bell folds inward, the tentacles shorten, and the jellyfish becomes a smooth floating pearl. Over days or weeks, that pearl anchors to a surface, sprouting the stems and buds of a new colony. From that colony, new jellyfish emerge, identical to the one that seemed to die. Each generation is the same individual, repeating itself in an endless loop of renewal. To humans, it sounds like immortality. In truth, it is something quieter and stranger, a balance between fragility and endurance. The jellyfish can still be eaten, crushed, or carried away by currents. It does not live forever in the way stories imagine. Instead, it survives by retreating from death, folding backward through time to a state that allows it to begin again. It is not immune to endings, only patient enough to outlast them. The energy cost of this cycle is high. Rebuilding a body requires effort, and effort requires food. The jellyfish performs its renewal only when the alternative would be final. It saves its secret for the last moment, as if life itself were waiting for a signal to begin the story again. In this, Turritopsis reveals something that most creatures cannot do, an awareness written not in thought, but in chemistry. Its cells sense collapse before it happens, and they answer by rewriting themselves. Scientists who study its biology are still uncovering the details of how it happens. Within its tissues, certain genes turn on that are usually silenced after early development. These genes unlock the ability to rebuild. They allow adult cells to return to their embryonic state, guided by chemical messages that tell each cell what to become. In laboratories, researchers have traced these changes step by step, hoping to understand how age and identity can be reversed. The jellyfish is not only a curiosity, but a window into the deep machinery of life itself. The simplicity of its body hides a sophistication that rivals the most complex forms. With no brain, no heart, and almost no organs, it has found a path to permanence that eludes everything larger. Its survival is not through strength or intelligence, but through flexibility. In a world that constantly changes, it endures by changing with it. Where most life resists decay until the end, this jellyfish accepts it, dissolves, and then rises again. The discovery of its regenerative power reshaped the way biologists think about aging. In every animal, aging is the slow accumulation of damage. Cells divide, errors appear, and systems falter. Yet here is a creature that can wipe the slate clean, undo the damage, and start fresh. The principle is not eternal youth, but eternal renewal. If such a mechanism exists in something so small, it suggests that the potential for rejuvenation is not a miracle, but a possibility, one that life may have used before and hidden away. In the deep, the immortal jellyfish continues its silent loop. It drifts with the plankton, its bell pulsing rhythmically, catching tiny prey in its trailing threads. When it is hurt or starved, it curls inward and falls again, beginning its transformation. Beneath it, colonies of its own former selves cling to rock and sand, waiting to send new versions into the water. There is no single individual, only continuity, an unbroken line of living light. Each pulse of its body is a quiet defiance of time. Around it, larger creatures are born and die, cycles of life measured in breaths, migrations, or seasons. The jellyfish floats between them, unchanged, repeating. It does not conquer death, but moves past it, finding space between endings and beginnings. In the rhythm of the sea, its pulse becomes one more heartbeat, steady, translucent, and unending, proof that even the most fragile life can learn the oldest secret of all, to begin again. Some monuments sink by accident, others by design, but a whale's fall is life returning home. It begins at the surface, often without witness. A whale exhales one final plume, its great lungs emptying as the body grows still. Then, as gases escape and buoyancy fades, it turns downward and begins to drift. The fall is slow, a spiral through the deep, the vast shape turning gently as it descends into blue. What was once a mover of oceans becomes a traveler towards silence. The journey downward can last for days. As the whale falls, smaller creatures gather along the invisible scent trail that follows it, drawn from miles away. The first arrivals meet it while it is still descending, sharks and hagfish, feeding as they fall beside it, tearing into the softening flesh. When at last the body reaches the seafloor, it lands quietly, sinking into the fine sediment like a meteor that strikes without noise. The surrounding darkness folds around it. Within hours, the transformation begins. The first phase, called the mobile scavenger stage, is a frenzy of life in a place that rarely sees such abundance. Sleeper sharks, rat tails, and giant isopods arrive to feed, joined by eelpouts and amphipods that wriggle into every crevice. In a few months, nearly all flesh is gone. What remains is a bare skeleton, clean in places, ragged in others, resting in stillness after the storm of feeding. The second phase begins as bacteria bloom around the bones. Invisible workers multiply in the water and in the sediment, breaking down the oils and proteins that still linger. The seafloor darkens, stained by the chemistry of decay. Hydrogen sulfide and methane begin to seep upward, and the water around the carcass changes. This chemical transformation marks the enrichment phase. What once was death becomes fuel. The ocean's smallest inhabitants awaken to the scent of sulfur and feed upon the invisible feast. Over years, the whale's bones settle deeper into the mud. Their weight presses channels and hollows into the sediment, creating new microhabitats. Tube worms begin to appear, then mussels and snails, forming a dense community over the remains. Among them bloom creatures unlike anything on the surface. The ossidax worms, pale, root-bodied animals with no mouths or stomachs, colonize the bones directly. They send down thread-like roots that dissolve the calcium, tapping into the stored fat and protein within. Inside their tissues live bacteria that share the harvest. The worm's delicate red plumes wave gently in the dark water, turning decay into quiet color. Around the skeleton, new settlers arrive. Brittle stars stretch their arms across ribs, and small crabs pick through silt for scraps. Clusters of limpets and clams attach to exposed bone, feeding on the bacterial mats that coat its surface. Each layer of the whale's remains becomes a platform for new life, from microbes to invertebrates to fish. A whale fall becomes a living landscape, its bones serving as scaffolding for a slow, luminous ecology. Decades can pass this way. The final stage, when even the bone lipids are exhausted, is quiet. The worms thin out, the mats fade. What is left is pale and smooth, a skeleton polished by the currents, slowly vanishing into silt. Yet even then, the chemical imprint remains in the sediment, a lingering memory of the energy once released. For the creatures that thrive there, the whale fall was not a grave, but a world. Scientists studying these sites often describe them as cities of the deep, built not by design, but by the steady logic of life reclaiming what it can. Around a single whale, hundreds of species have been recorded, some found nowhere else. The whale's body, which once crossed oceans alive, now nourishes an entire ecosystem for half a century or more. The energy stored in its tissues, gathered over a lifetime of feeding and migration, returns to the sea in layers, first as flesh, then as oil, then as chemical breath. The chemistry itself resembles that of other deep oases like hydrothermal vents. Sulfide-rich plumes rise, feeding bacteria that use minerals rather than sunlight for energy. The deep sea, barren to human eyes, becomes vibrant wherever such chemistry takes hold. For this reason, whale falls are often called stepping stones across the abyss, isolated islands where life gathers before drifting on. Each fall reshapes the local ecology, ensuring that even in the most silent depths, new beginnings are always unfolding. When submersibles visit these sites, the view is both intricate and serene. The ribs arch like bridges, and clouds of small amphipods drift through them like dust motes in a dark cathedral. Nothing about the scene feels morbid. Instead, it hums with patient order. The whale's body, once lifted by lungs and muscle, has become part of the larger breathing of the sea. Above, the surface moves on, the ocean bright and restless as always. Below, in the cold stillness, A skeleton glows faintly with life, a quiet constellation on the seafloor. The whale's fall is not an end but a return, a transformation written in slow, deliberate stages. In giving itself back to the deep, it becomes what it always was, part of the ocean's endless circle of change, drifting toward forever, with nothing wasted, nothing truly gone. At the deepest edge of the ocean, where light has never arrived and the pressure could flatten steel, the water still carries traces of us. It drifts in threads too small to see, weaving through the silence, settling among the cold minerals of the abyss. Even in the quietest dark, the ocean carries pieces of us, drifting where no hand has ever reached. When researchers sent deep diving probes into the Mariana Trench, they expected to bring back creatures untouched by the modern world. The amphipods they caught were tiny, shrimp like scavengers, pale and translucent, adapted to the weight of 11,000 meters of seawater above them. Their bodies were simple, soft, and ancient in design, descendants of crustaceans that had roamed the ocean floor for millions of years. But when the scientists looked closer, under the microscope, they found color. Threads of red, blue, and clear plastic ran through their bodies like strange veins. The discovery came in the year 2019 when teams analyzing deep sea amphipods from the Mariana Trench, the Kermadec Trench, and other Hadal zones compared their stomach contents. Every single specimen contains synthetic fibers, fragments of nylon, polyethylene terephthalate, and polyester. These were not intact objects but microfibers, the dust of the modern world. They had once been clothing, packaging, rope, or nets. Each fragment was smaller than a grain of sand, yet sharp enough to pierce tissue and fine enough to sink past light itself. Plastic does not vanish, it only changes shape. Sunlight breaks it, waves grind it, and microbes nibble at it, but the molecules remain. Polymers that once floated in sunlight become particles that fall through shadow, carried by the slow rain of detritus that feeds the deep. Fish eat them, plankton trap them, and when those organisms die, they descend, carrying the debris downward. Over decades, each piece falls farther, tumbling through the twilight and into the trenches, where it joins a sediment of glass, dust, and bone. The amphipods do not choose this meal. They eat what comes, as everything in the deep must. They are scavengers of the planet's leftovers, the last link in a chain that begins with sunlight and ends with decay. But now the chain contains something new. When the amphipods die, the plastic remains inside them, waiting for the next creature to arrive, to feed, to carry the fragments forward once more. In this way, the ocean has built a new kind of circulation, not of nutrients, but of permanence. The ocean floor, long thought to be the planet's final resting place, has become a record of our chemistry. Sediment cores taken from the deep Pacific show layers of microplastics settling alongside volcanic ash and plankton shells. In some places, the concentration reaches thousands of particles per kilogram of mud. The pieces are not all the same. Some are translucent fibers from washing synthetic fabrics. Others are microscopic shards of fishing line or packaging film. Each fragment tells a story of origin, from a factory, a household, or a storm drain that met a river and kept moving. Plastics fragment endlessly, but never truly decay. Their bonds resist the natural processes that break down organic matter. Bacteria may scuff their surfaces, ultraviolet light may bleach them pale, but the molecular chains remain intact for centuries. The smallest pieces, called nanoplastics, are invisible even to most microscopes. They drift like dust inside the water itself, impossible to separate from the element they now inhabit. In the still water of the trenches, where circulation is weak and time moves slowly, the plastic settles. It becomes part of the geological future. Some fragments fuse with minerals and shells to form plastic glomerates, stones of mixed origin that will harden into the strata of tomorrow. Scientists call them anthropogenic fossils, evidence that the Earth has entered an age shaped by its own inhabitants. The discovery of microplastics in the Hadal Zone has changed how researchers think about the deep. For decades, it was imagined as a sealed world, insulated from the noise of the surface. Now, every trench and basin is known to be connected, carrying traces of the same material that surrounds cities and shores. The boundary between human and natural has dissolved into molecules. In the laboratories that study these samples, the work is quiet and methodical. Each fiber must be isolated, measured, and tested to identify its polymer type. Instruments heat the material to trace its chemical signature. What emerges is not a message of disaster, but of reach, a recognition that no part of the planet stands apart anymore. The same carbon bonds that made plastic useful have carried it into every ecosystem on Earth. Above, waves break against coasts lined with foam and driftwood. Below, amphipods continue their patient work, digesting what falls from the light. The plastic within them is colorless here, a part of the sediment's fine dust. Over time, it will be buried deeper, pressed between silt and shell, and one day perhaps turn to stone. The deep ocean was once thought to be a place of origin, where life began in chemical heat. Now it also holds the quiet residue of what life has made. No current can carry it away, no darkness can hide it. Even at the bottom of the world, the ocean keeps what it is given, folding it into the slow heartbeat of the earth itself. Beneath the wide stillness of the ocean lies the Earth's largest and least seen workshop. Down where the light fades and the temperature drops toward freezing, the seafloor is never truly quiet. It stretches, fractures, and reforms, a restless skin that renews itself grain by grain. The ocean hides more than 1 million volcanoes, each one part of a planetary rhythm that never stops. Together they trace lines across the globe like seams on a living sphere, shaping the foundation of every continent and island that has ever existed. These volcanoes do not roar or glow as those on land do. Their work is slower, steadier, and older. Beneath several kilometers of water, molten rock pushes upward through cracks where tectonic plates drift apart. The heat that escapes here comes from deep within the mantle, carried by slow convection currents that turn the planet from within. When this molten rock reaches the surface of the seafloor, it cools instantly, meeting water just above freezing. The contact turns lava into rounded shapes called pillow basalts, stacked like smooth bubbles of glass. These build the newest crust on Earth, a continuous layer that grows by inches each year. This slow production of new crust defines the mid-ocean ridge system, the single largest geological structure on the planet. It winds unbroken for more than 40,000 miles, looping through every ocean basin. The mid-Atlantic ridge alone rises from the seafloor like a submerged mountain chain, higher and longer than the Himalayas. From space, it would appear as a pale thread crossing the blue, a faint scar where the world remakes itself day after day. The process is not violent so much as steady. Lava flows quietly in the dark, spreading outward, cooling and hardening. As it does, magnetic minerals within the rock align to Earth's field, freezing a record of its direction at the moment of formation. Over time, this produces symmetrical patterns on either side of the ridges, stripes that tell the story of plate motion. These magnetic signatures, first mapped in the mid-20th century, confirmed what scientists had long suspected. The continents move because the seafloor itself grows. Around the edges of these ridges, life has found unlikely footholds. Where seawater seeps into cracks and meets magma below, It superheats and returns to the surface as hydrothermal fluid. The water bursts out from the seafloor in clouds of black or white mineral smoke, building chimneys of iron, sulfur, and silica. These vents form small but intense ecosystems, sustained not by sunlight but by chemistry. Bacteria harvest energy from the minerals, forming the base of a food web that supports worms, shrimp, and crabs. Even in darkness, the heat of the earth feeds life. Most of the volcanoes never rise high enough to be noticed from the surface. They remain seamounts buried under pressure and time, yet they are far from lifeless. Their slopes gather coral and sponge colonies that cling to stone like forests of glass and color. Each ridge and crater becomes a habitat, sculpted not by erosion, but by creation. In this way, volcanic activity beneath the sea supports entire ecosystems, from microbial mats to deep sea coral gardens that can live for thousands of years. Scientists mapping these regions rely on sonar and remote submersibles to see through the dark. The images that return show a landscape that is at once alien and familiar. Long valleys where plates diverge, sharp cliffs where lava once surged, and broad plateaus newly born from molten flow. Occasionally, satellite data reveals small changes in sea level above these ridges, tiny swells or dips that betray eruptions too deep for light to catch. These signals, though faint, mark the continual creation of new Earth. The minerals released by this activity travel far beyond the vents. Iron, manganese, and other elements drift upward and outward, carried by ocean currents that fertilize the upper layers of the sea. Plankton bloom where volcanic dust settles, feeding fish and whales that will never know the source of their nourishment. The chemistry of life on the surface is tied, invisibly, to the fire below. Over centuries, this hidden construction reshapes coastlines and shifts ocean basins. As new crust forms, old crust sinks into trenches elsewhere, melting again into magma. It is a cycle without pause or endpoint, the same pulse that has been at work since the Earth first cooled. The continents ride on this slow tide of rock, drifting over a mantle that never rests. Sometimes, however, the boundary between unseen and visible blurs. A volcano near the surface may push high enough that its summit pierces the waves. For a short time, it forms an island, steaming and unstable. Then, as erosion and waves reclaim it, the new land disappears again beneath the water. These fleeting islands are reminders of the ceaseless work below, each one a brief glimpse of creation made visible. Hidden volcanoes are not anomalies, they are the planet's heartbeat. They knit together the crust, balance its temperature, and set the stage for the landscapes above. Every ridge, every vent, every plume of mineral smoke is part of a single continuous act of renewal. This constant reshaping beneath calm waves builds the stage for sudden creation, like the newborn island we will soon meet. In the shallow turquoise waters of the Bahamas, where sunlight dances on white sand and coral reefs glow with color, there are places where the sea suddenly falls away. From above, they appear as perfect circles of deep blue, framed by the pale greens of the surrounding shallows. These are the blue holes, vast sinkholes that plunge straight down into darkness. They are entrances to another world, places where time has layered itself in quiet spirals of sediment and stone. Each blue hole began long before the islands were islands. During the ice ages, when sea levels were much lower, the land now hidden beneath the waves was exposed to wind and rain. The limestone bedrock of the Bahamas, porous and soft, dissolved slowly as fresh water carved passages through it. Caves formed underground, their ceilings growing thin until they finally collapsed, leaving circular openings that descended into the earth. When the glaciers melted and the seas rose again, the ocean flooded these caverns. What had been hollow chambers in stone became deep blue wells filled with salt water, still connected to the sea through unseen cracks and tunnels. From the surface, a blue hole looks calm and inviting, the water so clear that the edges blur into the sky. But as divers descend, the light fades quickly, the walls narrow, the temperature drops, and the color shifts from turquoise to cobalt to near black. At a certain depth, usually around 100 feet, the air itself changes. A thin milky layer marks the halocline, the boundary where warm seawater meets colder freshwater. It shimmers like glass, bending light and creating a mirage of reflection beneath the diver's fins. Below that lies a heavier layer filled with hydrogen sulfide, a poisonous gas formed by bacteria feeding on organic matter. This layer smells faintly of rotten eggs and marks the start of a zone where almost no oxygen exists. The water there is still and ancient, untouched by currents. Anything that sinks into it, from plants to animal remains, is preserved in remarkable detail. The blue holes, in this way, have become natural vaults of time, silent archives recording thousands of years of life and climate. Within their sediments lie fossils of creatures that no longer exist. In the Bahamas, researchers have found bones of extinct crocodiles, giant tortoises, and early species of birds that once filled the island forests. Some skeletons are so intact that even delicate bones remain in place, protected by the anoxic water below. These remains tell stories of changing landscapes and shifting seas, of animals adapting and disappearing as the world's climate warmed and cooled again and again. The walls of the blue holes also preserve layers of mineral deposits that hold traces of the air and water from distant ages. Scientists studying these formations read them like pages of a slow moving book. Each layer captures the chemistry of the time it was formed, the salinity, the temperature, even the amount of rainfall. From these clues, researchers can reconstruct entire chapters of the Earth's climate history. They can see when the Caribbean was lush and humid, when droughts swept the islands, and when rising seas reclaimed the land. In the depths, strange life persists. Without light or oxygen, microorganisms have evolved to thrive on sulfur and iron, feeding on what little the chemical gradients provide. They form thin films on rock surfaces, painting the walls in shades of white and orange. These microbes resemble those found near hydrothermal vents deep in the ocean, suggesting that life's adaptability knows no boundaries. Some scientists believe that such ecosystems may even resemble what could exist beneath the icy crusts of moons like Europa or Enceladus, life sustained by chemistry, not sunlight. For divers, entering a blue hole feels like leaving the world behind. The water muffles all sound, and the deeper one goes, the more the outside fades away. Beams of light from the surface shrink into narrow columns, casting faint silver on the limestone walls. In that silence, it is easy to forget that these places connect directly to the ocean through unseen channels that twist and turn beneath the sea floor. Tides breathe through them, drawing water in and out like the slow pulse of the earth itself. Some blue holes, like Dean's Blue Hole on Long Island, reach depths of more than 600 feet, making them among the deepest in the world. Others are smaller, hidden in mangroves or inland lagoons, their surfaces covered with leaves. Each one holds its own balance of gases, water, and history, each one a sealed fragment of the planet's memory. In their layers, scientists have found pollen from ancient forests, dust blown from continents, and chemical traces of storms that passed thousands of years ago. The blue holes are not only geological wonders, but also quiet storytellers. They show how the Earth keeps its records in unexpected places, in stone dissolved by rain, in sediments pressed by time, in water that has not been disturbed for millennia. The Bahamas may appear sunlit and new, but beneath its bright surface lies an archive older than any civilization, written in layers of rock and silence. When the tide moves, the blue holes breathe softly, drawing in salt water and exhaling fresh water through unseen veins in the limestone. They are living scars of the planet's past, their depths holding the memory of a world that keeps remaking itself, one slow collapse, one rise, one layer at a time. At night, when the wind calms and the sea lies perfectly still, there are places on Earth where the water begins to glow. A single touch sends ripples of light outward, each wave a brief shimmer of electric blue. A fish passing near the surface leaves a trail like liquid fire. The paddle of a boat becomes a brush painting on darkness. These are the bioluminescent bays, quiet lagoons where millions of microscopic lives turn motion into light. The glow begins inside cells, too small to see. They belong to single-celled plankton known as dinoflagellates, organisms that drift with the tides and live by day on sunlight and nutrients from mangrove leaves. Each carries two fragile molecules within its body: luciferin, a compound that produces light when it reacts with oxygen, and luciferase, the enzyme that triggers that reaction. When the cell is disturbed by touch or vibration, the two meet. The result is a flash of cool blue light that lasts less than a second, so brief that it feels like the sea itself is breathing. The reaction is entirely chemical, a precise balance of energy and control. Unlike fire, it releases no heat. It is light without flame, life translating motion into radiance. The color, always blue, is not an accident of beauty, but a function of physics. Blue wavelengths travel farthest through seawater, cutting through depth and murk better than any other hue. Nature chose this color because it reaches the farthest, making the signal visible even where no sunlight can follow. The purpose of the glow remains partly a mystery. Some scientists believe it serves as a defense, startling predators or drawing larger hunters toward those that threaten the plankton. Others think it may be a kind of signal, a silent flash to warn, attract, or coordinate among drifting colonies. Whatever its reason, the effect is universal. Each spark is a response to stress, a survival reflex that, seen at scale, turns an entire body of water into something ethereal. There are only a few places on the planet where this light gathers in such density that it transforms the sea. The Caribbean holds several of them: Mosquito Bay on Vieques Island, Luminous Lagoon in Jamaica, and the sheltered inlets of the Bahamas. By day they appear ordinary, shallow and calm, lined by mangroves and stirred by warm breezes. But when night falls and the moon hides, the transformation begins. Step into the water, and the shallows bloom with color. Each movement awakens countless sparks until the bay itself glows like a piece of the sky turned upside down. The secret lies in the stillness. These lagoons are nearly closed systems, their narrow mouths restricting flow to the open sea. The water stays warm, rich in nutrients from fallen mangrove leaves, and calm enough for dinoflagellates to accumulate in extraordinary numbers. Their concentration can reach hundreds of thousands per liter, dense enough that even the faintest disturbance triggers a visible shimmer. It is a balance of biology, chemistry, and geography, a rare alignment of all three. The light, however, is delicate. It depends on a precise mixture of salinity, oxygen, temperature, and darkness. Change one too much, and the glow begins to fade. In recent years, the brightness of several famous bays has dimmed. Tour boats stir sediment and fuel into the water. Sunscreen chemicals and fertilizers drift from nearby towns. Artificial lights from shore disrupt the natural night that the dinoflagellates need to thrive. Rising temperatures and altered rainfall patterns shift the chemistry of the lagoons, sometimes replacing the glowing species with others that remain dark. Scientists studying these fragile waters call them living indicators. The brightness of the glow reflects the health of the ecosystem itself. The plankton flourish only when the mangroves are intact, the water clear, and the tides unpolluted. When one part weakens, the light dims. A fading bay does not just lose its beauty, it loses balance. The chemistry of luciferine and luciferase depends on oxygen, and oxygen depends on a living, breathing bay. Light here lives on a knife edge, bright only while the water stays pure. In Puerto Rico, Mosquito Bay still shines brighter than anywhere else on Earth. Its isolation and the protection of nearby mangroves have kept it alive. On moonless nights, the lagoon becomes a sheet of blue fire. The wake of a kayak spreads behind like a comet's tail, and every droplet that falls from a paddle bursts into light. Fish dart beneath the surface, leaving glowing trails that twist and vanish. To see it is to watch energy made visible, the raw interaction of life and motion in perfect rhythm. Bioluminescent bays are not just wonders of sight, but of survival. The same reaction that dazzles the eye has existed for millions of years, long before humans, perhaps even before the first eyes evolved to see it. Deep in the open ocean, countless species use the same chemistry, squid signaling through darkness, jellyfish pulsing under the weight of the sea, plankton drifting through midnight water. The bays are only the surface echo of that vast hidden light. What makes them special is their closeness to us, their ability to let a person stand waist deep and watch the ocean glow at a fingertip's touch. The light is fragile, but it endures because it is part of something older than change. In every flicker, chemistry becomes art, survival becomes beauty, and the sea reminds us that even in darkness, life never stops reaching for light. Just off the coast of southern Greece, where the Aegean folds into shallow blue coves, lies a ghost city visible through the water on a calm day. Streets, walls, and courtyards stretch in patterns too deliberate to be natural. This is Pavlopetri, a settlement more than 5,000 years old, the oldest known underwater city ever charted. It belongs to the early Bronze Age, a time when writing had barely begun, and yet cities already rose from stone. Unlike Heracleon's deep tombs swallowed by silt, Pavlopetri lies in shallow water, every street traceable by sound. The city rests beneath only a few meters of sea, so close to the surface that sunlight touches its stones every day. Its plan is astonishingly clear. Parallel roads, clusters of rectangular houses, open courtyards, and a waterfront aligned with what was once a small harbor. It looks less like ruins and more like a city caught mid-breath, frozen in the moment before the tide became permanent. Divers can swim along the main street, tracing its course with a fingertip, the faint edge of a wall running straight beneath their hand. The discovery came by chance in 1967. Marine archaeologist Nicholas Fleming was surveying the coastline near Elefanisos when he noticed regular lines on the seabed, angles and alignments no current could carve. When his team dived, they found a city grid etched into the limestone floor. Pottery fragments scattered among the stones dated the site to around 3000 BC, centuries before classical Greece. Pavlopetri was not myth, but memory preserved in salt water. For years, exploration depended on divers and sketches made by hand, each dive short and limited by visibility. Then, in the 21st century, new tools allowed the city to be seen as never before. Using underwater photogrammetry, archaeologists captured thousands of overlapping images that computers stitched into a seamless map. LiDAR scanners, mounted on small submersibles, traced every contour of the site to millimeter precision. The result was a three-dimensional digital reconstruction that revealed Pavlopetri's full extent, an urban plan covering nearly 10 acres of seabed, complete with avenues, courtyards, and stone thresholds still in place. In the reconstructed models, the city looks almost alive. Shadows move across its streets as virtual sunlight shifts, showing where walls once cast shade and where open squares caught the morning glow. Archaeologists can now simulate how its residents might have moved through it, how water flowed from cisterns to courtyards, and how trade goods passed from harbor to home. What once required imagination can now be measured and explored in full scale, a digital preservation of a city long surrendered to the tide. Pavlopetri's location tells much about its purpose. It sat at a crossroads of early trade routes between Crete and the mainland, connecting cultures that would later shape the Mycenaean world. Its people were seafarers and artisans. The tools and pottery found here speak of everyday life: storage jars for grain and oil, fine drinking cups, and small figurines that hint at ritual. Stone floors suggest permanence, while courtyards show that families lived in clusters, sharing space and work. This was no temporary outpost, but a thriving town built with design and memory. The city's end came slowly. Earthquakes cracked its foundations, and the land subsided. Rising seas crept inward, flood by flood, until homes stood waist deep and then vanished entirely. By around 1000 BC, Pavlopetri had disappeared beneath shallow water. Yet, unlike cities on land where war or rebuilding erased the past, the sea preserved its pattern almost perfectly. The same waves that buried it shielded it from plunder and decay. Modern researchers now use acoustic imaging to listen to what the eye cannot see. Sonar pulses travel across the site, bouncing back from stone edges and hollows to create maps precise enough to model every foundation. These soundscapes reveal hidden layers, small walls and rooms that lie beneath the visible ones, suggesting that Pavlopetri was built in stages over centuries. Each scan adds a page to a story written in limestone and silt. What sets Pavlopetri apart is its accessibility. On a calm day, swimmers floating above can see straight down to its streets, the geometry of a civilization lying in plain view. Fish glide through open doorways. Seagrass bends in slow currents where fire once burned. The play of light and water gives the ruins a strange animation, as if the city still breathes through the rhythm of the sea. The technology used here has changed how archaeology meets the ocean. 3D mapping allows researchers to revisit the site virtually, layer by layer, without disturbing the fragile stones. LiDAR reveals millimeter differences in elevation that the human eye would miss. Combined with drone imaging from above, these techniques create a complete digital twin of Pavlopetri, one that will endure even if the original continues to erode. Beneath the surface, the city endures in a kind of still motion. The water moves gently through its streets, tracing paths once made by footsteps. No storms disturb its quiet geometry. No walls have been rebuilt. No streets renamed. Pavlopetri remains as it was left, a small and precise reminder of how civilization began by the sea. It is both ancient and modern, drawn now not in stone, but in data, its map glowing softly on screens across the world. The sea took Pavlopetri, but in return, it kept it. Not as ruin, not as legend, but as evidence, a pattern of life so old it outlasted its own shore. In the middle of the South Pacific, between the quiet blues of Hunga Tonga and Hunga Hapai, the earth once exhaled so forcefully that it changed its own map. The sea above had seemed unbroken for centuries, a calm horizon stretching without hint of movement below. But beneath that stillness, magma was rising, gas was building, and the crust was beginning to flex. On a January morning in the year 2015, the first tremors reached the surface. At first, they were only murmurs, waves shifting without wind. Then the sea swelled and split. Columns of ash and vapor punched through the water, bursting upward in jets that pierced the clouds. Within minutes, the eruption was visible from orbit, an expanding bloom of darkness spreading across the blue. Satellites tracked every stage of the event in real time, the first complete record of an island being born. From above, the Pacific looked as if it had opened a wound. A ring of ash encircled the vent, while a plume climbed more than 30,000 feet into the sky. Lightning flashed within it, igniting the storm of its own making. Where there had been only open ocean, there was now land, raw, black, and still breathing. The volcano had erupted before, many times, but never like this. The vent lay in the shallow channel between the two older islands, forming what scientists call a caldera, a vast depression left by earlier explosions. When magma met seawater, it created a violent reaction known as a phreomagmatic blast, where steam expands faster than sound. Rock shattered into fine ash, fusing into a pale, powdery crust that began to cool into stone. Within days, the eruption slowed and the newborn island appeared. It rose nearly 100 meters above the sea, linking Hunga Tonga and Hunga Hapai with a new crescent of land just over a mile long. The air above it shimmered with heat, and the ground steamed as seawater trickled into cracks and boiled away again. Scientists reached the island within weeks. They stepped onto rock that was still warm to the touch, sulfur hissing from vents beneath their feet. The air smelled of minerals and burned air. The cliffs were soft, friable, built of volcanic tuff so light that it crumbled in their hands. Pools of turquoise water collected in craters where rain met hot ash. Even then, the island was already changing, its ridges slumping, its coastline redrawn by every tide. For geologists, it was a once in a lifetime event, a natural laboratory to watch land making in motion. NASA satellites and drones captured its growth from orbit, while researchers on the ground mapped the shape of its slopes using LIDAR and photogrammetry. They watched how the sea eroded the soft edges, how rain carved gullies into its heart, and how birds began to arrive long before plants took root. The formation of Hunga Tonga, Hunga Ha'apai, helped scientists understand how the world's earliest islands may have emerged from ancient seas. It also revealed how fragile such creations are. By late 2021, the island had begun to weather away, slowly dissolving under wind and waves. But the story was not over. On January 15th, 2022, the volcano awoke again, this time with almost unimaginable force. Pressure built within the submerged chamber until it burst in a single explosion, so vast it reshaped the atmosphere itself. Satellites recorded a shock wave racing outward at nearly the speed of sound, circling the planet multiple times. Sensors in Alaska, more than 6,000 miles away, felt the pulse. The blast sent plumes of ash 50 kilometers into the stratosphere and displaced millions of tons of water, generating tsunamis across the Pacific. When the sky cleared, the island was gone. Only fragments of its black cliffs remained, and the sea had reclaimed the rest. The eruption left a caldera nearly 5 miles across, its rim hidden just beneath the surface. What the planet had made in weeks, it had unmade in hours. The data collected from this sequence became invaluable. Atmospheric scientists studied the shockwave, which circled Earth at least 4 times. Oceanographers traced the tsunamis as they reflected around basins and shorelines. Geologists mapped the underwater crater, revealing collapsed ridges and a new landscape carved in molten relief. For all its destruction, the eruption left behind an extraordinary record of how violent creation can be. Yet even in its aftermath, there was quiet beauty. Satellite images taken days later showed a pale steam cloud rising from the still warm sea, glowing faintly in the early light. Around it, the ocean lay smooth, reflecting the color of the sky. Within that calm, the cycle had already begun again. Minerals leached from the eruption fed plankton blooms that spread across the surrounding waters, drawing life back to the surface. For 7 years, the island had existed as proof of the planet's ceaseless rhythm, a reminder that Earth's surface is only a temporary arrangement of heat and water. Its rise and fall were not separate events, but parts of the same breath. Within hours of its destruction, the newborn island steamed under the sun, proof that creation and loss, in the deep rhythm of the sea, are never far apart. The deeper the ocean grows, the quieter it becomes. Sound stretches thin, light disappears, and the weight of the world above presses down until even the strongest vessel would fold like paper. Yet, within that silence, machines now move where no human body could ever endure. They do not rush or falter, they drift, patient and unafraid, carrying the light of human curiosity into a place that has never known it. These deep sea robots are built not to conquer the abyss, but to listen to it. Each one begins its descent from a deck washed in salt and spray. Cables unwind slowly as the hull tilts with the sea. Then, without ceremony, the robot vanishes beneath the surface. The chatter of the crew fades to the hum of motors. The world above is left behind. Hours later, long after sunlight has dissolved into blue, the descent continues through layers of stillness. The pressure multiplies with every 100 meters, pressing against steel and titanium. Inside, the electronics hum with steady warmth. Some of these machines remain tethered to the ship by strands of fiber thinner than a finger, their signals carrying streams of images upward through the dark. Others move freely, guided only by algorithms and instinct, learning to navigate through the unbroken blackness on their own. Their design is a balance between strength and grace. Every curve, every joint, is shaped to survive under thousands of atmospheres of pressure. The lights they carry are narrow and focused, cutting a single cone through the void. Cameras adapted to the dark record, what no eye could ever see, unaided. The robots do not see in color as we do. They see in gradients of light, in texture, in heat, in the subtle motion of particles drifting like dust. The human connection never disappears. Above, on the ship, scientists sit before banks of monitors, watching through those distant eyes. They speak softly to one another, adjusting controls by millimeters, holding their breath as a mechanical arm reaches out to grasp a fragment of coral or the shell of a creature no one has named. Some wait for hours for a single moment of movement, a flick of a fin, a cloud of silt, a life revealed. Each of these machines carries tools of astonishing precision. Arms tipped with delicate grippers can lift a specimen no larger than a pearl without disturbing the sediment around it. Sensors test temperature, acidity, and trace chemicals in the water. Small drills can extract samples from rock or sediment cores without breaking their structure. The robots operate not as explorers of conquest, but as caretakers, leaving almost no mark on the places they visit. Autonomous vehicles, unlike their tethered counterparts, must think for themselves. They chart courses through underwater canyons, adjusting to changing currents. Machine learning helps them recognize patterns of life or signs of volcanic activity. They can follow faint plumes of chemical change, tracing them back to their source like detectives in the dark. Over time, they learn what to notice and what to ignore, their perception sharpened by thousands of dives. What they find often feels like glimpses into another planet. A ghostly octopus brooding her eggs on a rocky ledge. A fish with skin so transparent that its bones shimmer inside it. Gardens of glass sponges rising like frozen smoke from the seafloor. Sometimes they stumble upon things older than life itself, ancient manganese nodules growing grain by grain across millions of years, or the skeleton of a whale slowly dissolving into dust, feeding an entire city of worms and crabs. To witness such things requires patience of an uncommon kind. The dives last for hours. The footage streams in silence, Nothing moves quickly in the deep. Even the smallest detail, a slow exhalation from a vent, a shimmer of light from bioluminescence, feels monumental when seen against the endless stillness. For the scientists who watch, it is a kind of meditation. Each frame is a reminder that discovery can be as quiet as a single flicker in the dark. Sometimes the robots find what humans once left behind, the remains of ships that vanished into storms, aircraft swallowed by time, or fragments of debris that drifted down from the surface. They pass these things without judgment, recording what is there, capturing the intersection of history and nature with the same calm precision they give to living things. The data they return with is immense. Terabytes of imagery and samples travel back to laboratories, where each pixel and specimen tells another part of the story. But what lingers most is not the information, it is the sight itself. The realization that through machines made of metal and code, we have extended our senses into a realm that would destroy us in seconds. The ocean's depths were once thought unreachable. Now they are places of quiet collaboration between human patience and mechanical endurance. These robots do not replace the explorers who watch them, they extend them, translating human wonder into light and movement. Through their lenses, we learn to see where eyes alone would break. Far below the surface, beyond the reach of waves and storms, the ocean moves in silence. It flows not as a single body, but as a vast network of invisible rivers, connecting every sea on Earth. These deep currents travel slowly, winding around continents, rising and sinking with the weight of salt and the pull of temperature. Together, they form what scientists call the thermohaline circulation, a global conveyor belt of water that never stops turning. The movement begins in the coldest corners of the planet. Near the poles, seawater cools until it grows heavy enough to sink. When sea ice forms, the salt that was once part of the water is pushed away, leaving behind liquid that is even denser. This dense water slips downward, sinking to the ocean floor like smoke falling through air. From there, it begins a long journey, sliding south along the seafloor, crossing basins and ridges in darkness that no light ever reaches. At the same time, in warmer parts of the world, surface water heated by the sun grows lighter. It spreads outward, moving toward the poles where it will eventually cool again. This endless cycle of rising and sinking, heating and cooling, drives the flow that connects the Atlantic, Pacific, Indian, and Southern Oceans into one continuous system. It is slow, so slow that a single particle of water may take 1,000 years to complete the full circuit. Yet it is constant and steady, like a heartbeat that the planet depends on. Temperature and salinity are the two forces that guide it. Warm water holds less salt and floats higher, while cold water holds more and sinks. The balance between these two properties decides how water moves, how fast it travels, and how deep it flows. In places like the North Atlantic, this balance creates one of the strongest downward currents in the world. There, icy winds from the Arctic strip heat from the sea, and the surface water becomes dense enough to fall. As it sinks, it drags surrounding water with it, setting the global conveyor in motion. The path of this deep current winds through the ocean like veins through a living body. It carries not only water, but also heat, oxygen, and nutrients. As it moves, it mixes layers that would otherwise remain separate. The deep ocean, cold and dark, depends on this motion to bring in fresh oxygen from the surface. Without it, much of the seafloor would fall silent, starved of the gases that sustain life. The circulation keeps the world breathing, though its rhythm is almost too slow to notice. At the surface, the same movement carries warmth across the planet. The Gulf Stream, a powerful current born from this larger system, brings heat from the tropics to the northern Atlantic, softening the climates of Europe and North America. Without it, winters there would be long and bitter, and much of the land would lie beneath snow. Farther south, cool water rising from the deep brings nutrients to the surface, feeding blooms of plankton that support entire food chains. The smallest drifting organisms depend on the same process that shapes storms, winds, and seasons. From space, satellites can see traces of these movements in the way the ocean's surface changes color and temperature. Swirls of warm and cold water twist around each other like smoke on air, showing where deep water rises and where it sinks again. Scientists use floating sensors and robotic instruments to follow these hidden paths, measuring the slow pulse of the ocean as it moves heat around the globe. The data they collect reveal how delicate the balance truly is. Even small changes in temperature or salinity can shift the flow, slowing or speeding the movement that keeps the climate stable. There have been moments in Earth's past when the conveyor nearly stopped. During ancient ice ages, when melting glaciers poured fresh water into the ocean, the sudden drop in salinity weakened the current. The deep water no longer sank fast enough to drive the cycle, and large parts of the Atlantic grew still. The atmosphere changed in response. Temperatures dropped, weather patterns shifted, and entire ecosystems were rearranged. It took centuries for the circulation to recover. Today, scientists watch carefully for similar signs. As glaciers melt and rainfall patterns change, fresh water once again enters the ocean in vast amounts. The thermohaline system adjusts quietly, its immense motion bending under the weight of the modern world. It is not a process that stops easily, but it is one that can slow, and a slower ocean means a slower transfer of heat, oxygen, and life. The rhythm that has guided the planet for millions of years listens now to our influence. Still, the conveyor moves. Beneath ships, beneath storms, beneath even the stillest calm, it flows on, unseen and unbroken. It threads the continents together, tying the poles to the equator, the surface to the seafloor. The water that sinks in the cold north will one day rise again in warmth somewhere far away, carrying with it the memory of where it has been. The planet breathes through this slow circulation, a silent motion that keeps the world alive, patient and enduring, beneath the waves. Across the ocean floor, where the light thins to twilight and sound moves with the patience of stone, rest the remnants of machines built for the air. They are scattered in quiet fragments, fuselages lying on their sides, wings half buried in sand, propellers curled like flowers made of metal. Once, these aircraft traced paths through the sky, their engines roaring, their bodies gleaming. Now they are still, the air replaced by water, the speed replaced by silence. These wrecks are not rare. The sea holds thousands of them, lost to time, weather, and war. Some slipped beneath the surface in combat, others in storms or mechanical failure, and some vanished so completely that their existence is remembered only when a diver's light reveals them again. The ocean floor keeps them as it keeps everything that falls to it, not in mourning, but in transformation. Unlike the ships that sank whole and heavy, airplanes bring a different kind of decay. Their thin aluminum skins, their precise rivets, and composite alloys face a chemistry far harsher than the air they were built for. Salt water begins its work immediately. Chloride ions seep into seams and joints, breaking down protective coatings, reacting with oxygen to create pale blooms of corrosion. Over months and years, the metal's surface softens, turning white and granular. Wings once silver now bloom with white oxide, a slow chemistry painting war into reef. The reaction forms layers that flake away, exposing new metal beneath, each surface surrendering again to the water's quiet insistence. Magnesium parts dissolve fastest, fizzing away in ghost-like patterns. Steel bolts turn to threads of rust that coil through the sediment. Even titanium, so strong on land, shows faint etching where the salt persists. This process is not destruction alone. The decaying metal feeds life, both chemically and physically. As the surface roughens, bacteria settle, forming thin biofilms that hold oxygen and nutrients. Corals and sponges find grip on what was once smooth. Over time, an airplane becomes scaffold and shelter, a skeleton for new ecosystems. The elements of alloy and mineral leach into the water, balancing local chemistry in subtle ways. Calcium from paint, iron from bolts, and aluminum oxides from frames all mix into the slow exchange of the seabed. Scientists studying these submerged plains see not only relics of history, but laboratories of chemistry. Each wreck corrodes differently, depending on the depth, temperature, and salinity of the water. In the warm shallows of the Pacific, oxidation races forward, covering aircraft in colorful crusts of coral and algae within decades. In the cold, still basins of the Atlantic, corrosion slows to a whisper, paint lingers, markings remain. Even the smallest etchings in the metal can survive for generations, preserved by low temperatures and minimal movement. Marine chemists often study these wrecks to understand how different alloys endure under pressure and salt. Aluminum, which forms a protective oxide layer in air, becomes unstable in seawater. The chloride ions break through that barrier, producing pitted patterns like lace. These marks, when analyzed, reveal how long the wreck has rested, how the current flows around it, even the microbe species that have colonized its surface. Each plane carries a record, written in the slow language of corrosion. The transformation goes beyond chemistry. Currents gather silt around the frames, burying some planes almost completely while leaving others half exposed. Soft corals settle along leading edges of wings. Sea fans unfurl where radar antennas once stood. The outlines of landing gear and cockpit windows become faint mosaics beneath layers of sponge and sediment. To the untrained eye, they might look like natural rock formations, but under close inspection, rivet lines still trace the geometry of design. In certain Pacific lagoons, divers can still find aircraft nearly whole, sitting in shallow sand as if they had landed gently. The cockpits are open, the dials and levers dusted with silt. Small fish dart through the frames, their scales catching the faint shafts of light that reach this far. Crabs have taken residence inside engine housings. The turbines, long still, have become circular caves for shrimp and eels. Where aluminum once met air, now coral polyps pulse slowly, their colors muted by the depth. Every touch of water rewrites the plane's structure. The polished alloys designed to resist friction and flight become powdery and porous. Rivets loosen, seams widen. Eventually, the airframes collapse inward, flattening under their own softened weight. Yet even as the form fades, the chemistry continues. The aluminum oxide, stable and inert, joins the seafloor, adding new mineral layers to ancient sediments. The ocean, indifferent and precise, recycles the fallen metal into its own slow architecture. To the scientists who document these transformations, the graveyards of airplanes are both haunting and instructive. They show how human invention enters the planet's deeper cycles, how the materials of flight evolve into the textures of the sea. What once resisted decay now participates in it, surrendering not in defeat, but in quiet exchange. No ceremony marks this process, no sound carries it upward. The water absorbs every change in silence. If one could watch it unfold, year by year, the metal would seem to breathe, fading, reforming, and feeding life in invisible increments. The sea does not preserve, nor does it erase, it transforms. Each plane becomes less a relic than an experiment in time, each alloy another chapter in the story of what happens when human design meets the chemistry of the deep. What lies beneath is neither wreckage nor ruin. It is evolution by corrosion, life by oxidation, memory turning slowly into matter. The airplanes sleep in their quiet galleries, their wings outstretched in the dark, dissolving by the rules of a world that forgets nothing. The deeper you go, the more the sea forgets the sun. Blue fades first to gray, then to black, until the water becomes an endless dusk that no surface light can reach. Yet in that darkness, the ocean glows. It does not shine all at once, but in scattered pulses, as if the deep itself were breathing, a spark here, a slow shimmer there, each one alive. Here, light is language, spoken in flashes that mean hunger, warning, or love. No two speakers of this light speak it the same way. Some emit quick bursts, a nervous rhythm meant to confuse predators or court a mate. Others release steady glows that hover in the dark, patient and unblinking. Together they weave a living constellation that drifts and flickers with each passing current. The anglerfish is perhaps the most familiar voice in this silent conversation. Its body is built for invisibility, but from its head rises a delicate filament tipped with a glowing lure. The fish waits motionless, its light swaying gently like a fragment of the surface sky. To a smaller creature, the glow looks like food. When it approaches, the anglerfish's mouth opens in a smooth and sudden motion, swallowing its prey in a single quiet pulse. Down here, deception is illuminated. Elsewhere, the light serves the opposite purpose. The hatchetfish, silver and narrow as a blade, drifts through the midwater darkness with its belly lined in tiny lanterns called photophores. These emit just enough glow to mimic the faint glimmer filtering from the ocean surface above. When predators look up, the fish disappears completely into the light. This trick, called counterillumination, is one of evolution's most elegant defenses, a vanishing act performed with perfect control. Squid, too, have learned this craft. Some species can adjust their photophores individually, balancing brightness and angle like an artist mixing color and shadow. Others use bursts of light as a kind of coded signal. A single pulse might mean approach, another retreat, another a brief flash of threat. Researchers have recorded schools of squid moving in synchronized rhythm, their bodies flickering in patterns that seem almost like conversation. In this dark world, light defines everything that survives. The comb jelly, a drifting ribbon of glass, refracts even the faintest glimmer into waves of shifting color. As it moves, its cilia scatter the light into rainbows, painting its body with moving stripes of blue and green. The vampire squid releases glowing clouds of blue mucus when disturbed, a luminous distraction that buys time to vanish. Small shrimp burst in sudden flashes before darting into the sand, while worms spiral through the dark, trailing glowing threads that hang in the water like drifting filaments of silk. The deep ocean is a place where almost every creature glows, and each uses that light in its own way. Some use it to hunt, others use it to hide. Many use it simply to exist, to mark their presence in a world that otherwise offers no reflection. It is a vocabulary written in light, passed across millions of years, evolving in silence and pressure. To scientists, these glows are more than beautiful, they are data. The rhythm of flashing reveals how species interact. The brightness hints at depth, temperature, and even chemistry. A predator's lure may pulse faster in warmer water, while planktonic flashes rise and fall with the seasons. Researchers use sensitive cameras to record these patterns, then replay them in slow motion, decoding a language no human could ever hear. Even the smallest organisms join the dialogue. Tiny plankton drift through the upper layers of the ocean, glowing blue when disturbed. A wave breaking in the night or a dolphin passing through the surface can set them off, turning the water into rolling light. Ships leave glowing trails behind them, their wakes filled with microscopic sparks. Far below, giant siphonophores Colonies of thousands of small animals working as one pulse in long chains of light that stretch for meters through the dark. The result is a choreography older than any species watching it. Submersibles that enter this realm must learn to listen rather than intrude. Their lights scatter the natural glow, so scientists often turn them off and wait. At first, there is nothing. Then, one by one, the sparks return. The darkness begins to breathe again. The observers watch through small windows as the black water turns softly blue, the living light moving around them like drifting stars. Unlike the steady burn of the sun, the light here is temporary. It flickers, fades, and returns, each flash a message written on the edge of survival. There is no waste in its making. Every pulse has purpose, even if that purpose is only to exist, to remind the deep that life is still here. When researchers describe what they see, they often fall silent halfway through. Words feel too solid for what moves before them. In a place where sight itself should fail, the ocean has built its own way to see. It speaks in flashes, in rhythms, in patience. The light of the deep is not brightness as we know it. It is memory, communication, and instinct intertwined. It flickers across the miles of dark water like thought itself, momentary, vital, alive. Above, the sea remains calm and still, but below the light continues, whispering in blue, telling stories in the dark that no surface has ever heard. Across the open surface of the sea, the world feels mapped and measured. Satellites trace every current, ships cross each latitude, and instruments reach through the water with signals that echo from the bottom. Yet for all this certainty, the ocean still hides more than it reveals. Beneath its calm surface lies an unfinished map, a world of silence that continues to build itself, quietly, in the dark. Scattered across this world are more than 3 million shipwrecks, each one a small interruption in time. They rest on sand and silt, half buried and unbothered, their wood softened, their metal turning slowly to dust. Some lie close to coasts once busy with trade and travel. Others rest in trenches where no light has ever reached. Together they form an accidental archive, one that records not the victories of exploration, but the moments when it failed. The oldest of these wrecks belong to wooden ships, vessels that once carried the earliest traders and travelers between the islands and continents of the ancient world. Many were lost within sight of shore. In the Mediterranean, divers have found hulls still filled with amphorae, jars that once held oil, wine, and grain. In the Black Sea, the lack of oxygen has kept ships almost perfectly preserved, their ropes still coiled, their masts still standing. These wrecks have survived longer underwater than they ever did above it. The ocean, indifferent and patient, became their final harbor. As centuries passed, the ships themselves changed. Wood gave way to iron, sails to steam, and navigation by stars to navigation by signal. Yet the sea remained the same. It swallowed the great liners and warships of the modern age just as easily as the fragile boats before them. The Titanic, the Lusitania, and the countless submarines that vanished during 2 world wars are now part of the same submerged landscape. Their technology is gone, but their forms endure, resting in quiet lines of shadow that stretch across the seabed. The difference between the past and the present lies in how we find them. Today, sonar paints the ocean floor in bands of color. Robots glide through the dark, tracing outlines of ships with gentle beams of light. In recent years, explorers have located vessels thought lost forever: the Endurance beneath Antarctic ice, the Indianapolis deep in the Philippine Sea, the Franklin ships of the Arctic. Some were discovered through years of methodical searching, others appeared by chance, caught in the path of a survey, their shapes barely distinguishable from the rock around them. Each one changed what we thought we knew about where history ends, But even these discoveries are only fragments. For every wreck mapped and named, thousands more remain hidden. Storms erase their coordinates, currents scatter their debris, and time pulls them deeper into the sediment. The ocean folds them into its layers, stacking centuries upon centuries of forgotten travel. Wooden hulls become reefs, iron decks crumble into fine red dust, and glass windows turn opaque with salt. The distinction between artifact and landscape fades until what was built becomes part of what was born. Scientists studying these wrecks often speak less about history than about chemistry. In warm tropical seas, bacteria eat away at iron and steel, turning rivets into small colonies of rust. In colder waters, corrosion slows, preserving paint, ropes, and even fabrics for generations. Aluminum reacts differently from bronze, creating pale blooms of oxide that spread across the surface, like frost. Every wreck carries its own rate of decay, a timeline written not in years but in elements. The ocean is both sculptor and archivist, dissolving detail while recording form. To divers and researchers, these sites are not only ruins but habitats. Coral grows where rivets once held plates together. Anemones cluster along propellers. Fish dart through open windows that once framed a view of the sky. Even in silence, life reclaims the machinery of human progress, turning loss into structure. The frontier, it seems, is not empty at all. It is alive, moving, and self renewing. Still, what we have seen is only a fraction. Less than one-fifth of the ocean floor has been mapped in detail, and much of it only through distant sonar. Mountains taller than Everest lie beneath the waves, uncharted. Vast plains stretch between them, covered in sediment that no light has ever touched. There are trenches deep enough to hide entire ranges, places where sound moves strangely, and gravity itself bends. What lies there, wrecks, creatures, perhaps entire ecosystems, remains unrecorded, invisible to every map we have made. The paradox of the ocean is that progress always reveals more distance ahead. Each dive, each discovery, expands the outline of the unknown. Technology reaches farther, yet the horizon of mystery recedes just as quickly. The ocean's floor is not a boundary, but a doorway that opens in every direction. Its vastness does not end. It continues inward, downward, and across in ways that no single lifetime could measure. When explorers return to the surface, they bring with them hours of images, fragments of metal, and traces of sediment clinging to robotic arms. On the monitors, the wrecks appear like pale drawings in the dark. The frames are silent, the colors muted, but in that stillness, there is movement, slow, constant, endless. The ocean is not a place frozen in time. It is a place that keeps making time. The frontier is not far away or lost to time. It waits below, endless and unfinished, still unfolding beneath the quiet waves. The sea stretches endlessly, its surface rippling with light that hides everything beneath. For all the centuries we have looked at it, sailed across it, mapped its edges, we still know so little about what lies below. We have sent machines to other planets, watched distant moons through telescopes, and even reached the surface of Mars. Yet the ocean, the oldest part of our own world, remains mostly unknown. Beneath those waves lies a history older than the mountains, older than the stars we navigate by. Every discovery we have made beneath the surface has been a kind of remembering. The ocean does not forget. It keeps what falls into it, holding everything with patience. Lost cities, ancient forests, the bones of creatures long extinct, the wrecks of ships that once carried dreams and fear, all of it rests there. Layer upon layer of sediment becomes a record, each grain carrying the story of wind, rain, and time. The sea does not speak, but it remembers everything that has touched it. When we descend into its depths, we are not just exploring a place, we are traveling backward through the ages, through the memory of the earth itself. The fossils of ancient fish, the outlines of drowned coastlines, the remnants of coral reefs that lived when humans were still learning to walk upright, all lie beneath the water, undisturbed. The deep remembers not in words, but in silence, not in pages, but in pressure and darkness. The ocean is both past and future. It holds the remains of what once was, but it also carries the beginnings of what may come. The first life on this planet rose from its chemistry, from minerals and salt, from warmth and motion. Even now, in the cold vents of the deep, new forms of life continue to appear, born from heat and metal rather than sunlight. What began there billions of years ago is still unfolding. The ocean is an archive, but it is also an incubator, a place where creation never truly stopped. Above it, storms cross, ships travel, and satellites pass in steady orbits. But below, in that immense quiet, the earth breathes in slow rhythms. The currents move like the turning of time, pulling warm water into cold, mixing the living and the dead. Light fades, sound bends, and gravity feels different there. Every movement of the sea connects to something else. The tides that touch the shore, the winds that shape the clouds, the rain that falls on distant mountains. Nothing is separate. The same water that fills the deepest trenches will one day rise again as mist in the morning air. We have always been drawn to the sea, not only because it sustains us, but because it reflects something of ourselves. It is vast, unknowable, and full of stories we cannot see but can sense. The surface shows calm or fury, but beneath there is depth without end. It is the same with our curiosity, the need to understand what lies beyond reach. Every dive, every expedition, every question we ask about the ocean comes from that same quiet urge to know and yet still be humbled by what cannot be fully known. Technology lets us see more now than any generation before us. Robots drift through the darkness, mapping valleys no light has touched. Satellites trace the subtle movements of waves across the globe. We can listen to the echoes of whales as they call across thousands of miles. Yet, for all this progress, the more we learn, the more we realize how much remains hidden. Knowledge in the ocean is like light. It fades the deeper you go, and even where the light cannot reach, life continues, glowing softly, patient as time. Somewhere down there, beyond the line where sunlight dies, things still move and grow. Entire ecosystems live unseen, their chemistry foreign, yet familiar. The deepest trenches still cradle species we have never named, their shapes and colors unknown. Sound travels through those depths like a whisper through eternity, carrying stories we have not yet learned to hear. For every place we have touched, there are 1,000 still waiting. The ocean does not end, not truly. It only deepens, layer after layer, memory after memory. It holds our past, shapes our climate, and may hold the answers to futures we cannot yet imagine. It moves slowly, but it never stops. It has seen everything the earth has ever been and everything it might become. If you listen closely, when the waves settle and the world grows still, the sea seems to breathe, a long, steady rhythm that has never ceased. It does not call for discovery or fear. It simply waits. Somewhere below, beyond reach or sound, are the stories still untold, the forms still unseen, the beginnings still repeating. And as the world sleeps above it, the ocean keeps its quiet watch, holding its memories in perfect darkness. It remembers the birth of the planet, the first spark of life, the rise and fall of continents, and every moment in between. It does not need to speak, for everything it has ever known is still there, Written in salt, pressure, and silence, the sea remembers everything, and in that remembrance, it holds the wonder that keeps us searching.